Most people think they know what the universe is, a collection of stars and planets scattered across empty space, with clear boundaries somewhere far away. But the deeper scientists look, the more they discover that reality refuses to fit into simple boxes. What we call the edge of the universe isn't really an edge at all. What we imagine as empty space is filled with invisible forces we barely understand. Even the basic question of whether the universe has an end turns out to have answers that would have seemed impossible just a few generations ago. Time and again, our assumptions about the cosmos have been shattered by discoveries that revealed a universe stranger, larger, and more mysterious than anyone expected. We'll explore these mysteries in more depth in this video and discover just how much we still don't know. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. The universe extends in every direction around us, stretching far beyond anything we can truly comprehend. When we look up at night, we see stars, constellations, entire galaxies spinning through space. But if we could somehow travel faster than light itself, racing past every galaxy, every cluster of matter, what would we eventually find? This question has puzzled humans for centuries, and it touches something deep in our nature, this need to know what lies beyond the furthest boundary. Light from distant stars takes time to reach us. The light from our sun takes about 8 minutes to travel to Earth. Light from the nearest star beyond our sun takes over 4 years. From the most distant galaxies we can observe, light has been traveling for billions of years, carrying images of what those places looked like when the universe was much younger. This creates something scientists call the observable universe, a sphere of space containing everything we can possibly see. The edge of this observable sphere sits roughly 46 billion light-years away in every direction. That number might seem confusing at first, since the universe is only about 13.8 billion years old, but space itself has been expanding all this time, stretching the distance between objects, pushing that boundary further and further out. We exist at the center of our own observable bubble, not because we're special, but simply because that's how observation works. Every point in space sits at the center of its own sphere of visibility. Beyond this boundary, beyond what we can see, the universe likely continues. Most scientists believe it extends much further, possibly infinitely. There might be galaxies out there, billions of them, with stars and planets and maybe even life, but their light hasn't had enough time to reach us yet. In some distant future, as the universe ages, we might see further. New galaxies might drift into view as their ancient light finally arrives, but this raises another puzzle about boundaries and edges. If the universe does have a true edge somewhere, what would that even mean? An edge implies something on the other side, some space or void or completely different reality, beyond the last particle of matter. The human mind struggles with this concept because we're used to boundaries that separate one thing from another. A fence separates your yard from your neighbor's yard. The shore separates the ocean from the land. But what could possibly be on the other side of everything that exists? Some scientists propose that our universe might be curved in ways we can't directly perceive, just like the surface of a balloon curves through three-dimensional space. Our three-dimensional universe might curve through dimensions we can't experience. If you could travel in a perfectly straight line through such a universe, you might eventually return to your starting point, having circled all the way around without ever hitting an edge. Others suggest there might be multiple universes, entire separate realities existing alongside our own. In this view, what we call the universe is just one bubble in an endless foam of bubble universes, each with its own laws of physics, its own particles, its own story. The boundary of our universe might be like the skin of a soap bubble, separating our reality from countless others floating in some higher dimensional space. These ideas push us toward a strange realization about the nature of existence itself. We spend our lives surrounded by boundaries, walls, horizons, limits of all kinds. Yet the biggest boundary of all, the edge of everything, might not exist at all, or it might exist in ways so foreign to our everyday experience that we can barely think about them. There's something both humbling and oddly comforting in this uncertainty, this admission that even our most sophisticated instruments and theories leave vast questions unanswered. The cosmic microwave background radiation provides another clue about distant boundaries. This faint glow fills all of space, the afterglow of the Big Bang itself, stretched and cooled by billions of years of cosmic expansion. When we map this radiation, we see tiny variations in temperature, the seeds that grew into galaxies and stars. But the radiation appears remarkably uniform across the entire sky, suggesting that regions of space now separated by vast distances were once close enough to share the same temperature. This uniformity creates what scientists call the horizon problem. How did opposite sides of the observable universe end up at nearly the same temperature if they've never been in contact with each other? The most popular solution involves cosmic inflation, a period just after the Big Bang when space itself expanded faster than light, stretching a tiny uniform region into something much larger than what we can observe today. If inflation really happened, then our observable universe represents just a tiny patch of something vastly bigger, like seeing only a small section of an enormous painting. Dark energy adds another layer to this cosmic mystery. This invisible force seems to be accelerating the expansion of space, pushing galaxies apart at ever-increasing speeds. In the far future, billions of years from now, this acceleration might carry distant galaxies beyond our observable horizon. Stars and entire galaxy clusters might fade from view, not because they're dying, but because space is expanding so quickly that their light can no longer reach us. Future astronomers might look out at a much lonelier universe, seeing only the gravitationally bound galaxies in their local neighborhood. The question of what lies beyond also forces us to confront the limits of knowledge itself. Science advances by testing ideas against observations, forming theories that make predictions we can verify or disprove. But the truly distant regions of the universe, the places beyond our observable boundary, might forever remain beyond the reach of direct observation. We might develop increasingly clever ways to infer their properties, but we might never know with certainty what's really out there. Yet this uncertainty doesn't diminish the wonder of the question. In many ways, it enhances it. We exist as conscious beings in a universe that extends far beyond our ability to fully explore or understand. Every night, when we look up at the stars, we're seeing light that traveled across unimaginable distances to reach our eyes. We're connected to the most distant visible galaxies by threads of light, part of a cosmic web that might extend infinitely in all directions. Perhaps the most profound realization is that the question itself, this deep curiosity about what lies beyond, represents something remarkable about consciousness. Here we are, collections of atoms that somehow learn to think and wonder, asking questions about the ultimate nature of reality. The universe, through us, has developed the capacity to contemplate its own boundaries and mysteries. In pondering what lies on the other side of everything, we're participating in one of the deepest forms of cosmic self-reflection. The night sky above us tells a story about boundaries that don't quite work the way we expect them to. When darkness falls and city lights fade away, something remarkable happens to our perception. Stars begin to appear, one by one, then in clusters, then in such overwhelming numbers that the darkness itself seems to dissolve into light. Our minds naturally search for edges in everything we encounter. Tables have corners, books have covers, rooms have walls. This tendency runs so deep in human thinking that we automatically assume the cosmos must follow the same rules. Somewhere out there, we imagine, space simply stops. There should be a fence, a boundary, something that marks where everything ends. That the universe operates by different principles entirely. What astronomers have discovered challenges our most basic assumptions about limits and borders. The boundary we can observe isn't like stepping off the edge of a cliff or reaching the end of a road. It's something far more subtle and perhaps more profound. Light carries information across vast distances, but it doesn't travel instantly. Every photon that reaches your eyes tonight began its journey years, centuries, or millennia ago. The sun you see shining is actually the sun as it existed 8 minutes in the past. That's simply how long sunlight needs to cross the gap between our star and Earth. Consider the Andromeda Galaxy visible to the naked eye on clear nights as a faint smudge. The light entering your pupils right now actually departed from those distant stars over 2 million years ago. During that time, entire species have evolved and disappeared on our planet. The photons traveling toward us have been crossing empty space since before modern humans walked the Earth. This creates a fascinating paradox. The night sky functions as a vast museum of cosmic history. Nothing you observe in the heavens exists in the present moment. Everything is preserved light from the past, frozen in time during its long journey across space. Scientists refer to our cosmic viewing area as the observable universe. Picture yourself holding a flashlight in an enormous dark room. The beam illuminates only a circle around you, while the rest remains hidden in shadow. But instead of light revealing the darkness, time itself determines how far we can see. The Big Bang occurred roughly 13.8 billion years ago. Light from sources beyond a certain distance simply hasn't had enough time to reach us yet. This doesn't mean nothing exists in those unreachable regions. It only means we're blind to whatever might be out there. The situation becomes even more complex when we consider that space itself expands. Imagine drawing dots on a balloon, then inflating it slowly. From any dot's perspective, all the other dots appear to be moving away. No single dot occupies a special position, yet each one sees the same pattern of recession. This expansion means that light traveling toward us for billions of years has been crossing space that continuously stretches. The actual edge of what we can observe lies much farther away than simple mathematics would suggest. Current estimates place this boundary at roughly 46 billion light-years in every direction. Here's where the concept becomes truly mind-bending. This observable sphere centers on Earth, but it also centers on every other point in the universe simultaneously. An alien astronomer in a distant galaxy would see their own cosmic horizon, completely different from ours but following identical principles. The strangest aspect of this boundary is its invisibility. You could travel in a spacecraft for billions of years and never encounter a wall marking the edge of observable space. Galaxies would continue appearing in every direction, growing smaller and fainter with distance, until they merged into the background radiation left over from the early universe. This frustrates our desire for clear definitions. When we reach the edge of a forest, trees give way to open fields. When we arrive at an ocean shore, land meets water in an obvious line. But cosmic boundaries refuse to provide such satisfaction. They exist only because light has limits, and time has a beginning. Beyond our observable horizon, the universe almost certainly continues. The same physical laws that govern matter and energy here should apply in those unreachable regions as well. Galaxies probably spiral through space. Stars ignite and die. Planets form around suitable suns. Perhaps other forms of life peer into their own night skies, wondering about the nature of edges and boundaries. The observable universe represents just a tiny sample of what might exist. Within our visible patch of reality lie hundreds of billions of galaxies, each containing hundreds of billions of stars. The numbers grow so large they lose practical meaning. Yet, even this overwhelming abundance might be insignificant compared to what lies beyond our view. Some theoretical models suggest the universe extends infinitely in all directions. Others propose that space curves back on itself, creating a closed system with no true edges at all. We may never know which possibility describes reality, but the question itself reveals something important about human nature. We live within limitations while yearning to understand what lies beyond them. The cosmic horizon reminds us that boundaries often tell us more about the observer than about the thing being observed. What we call the edge of the universe is really the edge of our perception, determined by the speed of light and the age of everything we know. This perspective transforms our understanding of cosmic boundaries entirely. Instead of marking emptiness, the horizon suggests abundance. Instead of defining an end, it implies continuation beyond imagination. The edge becomes not a wall, but a window into the fundamental mystery of existence itself. Standing beneath the night sky, knowing that our view extends across billions of light years while remaining fundamentally limited, we face a profound philosophical puzzle. The universe reveals itself to us gradually, at the speed of light, one ancient photon at a time. We've created tools that can see things our eyes never could. There's something remarkable about pointing a telescope at what looks like completely empty space and discovering it's actually packed with thousands of distant galaxies. The darkness that appears vacant to us turns out to be teeming with entire worlds, each one containing billions of stars. When astronomers focus their instruments on these incredibly faint patches of light, they're actually looking backwards through time. The photons that hit those sensors have been traveling for billions of years, crossing unimaginable distances to reach us. Some of that light began its journey when the universe was still very young, when the first galaxies were just starting to form. The expansion of space itself stretches that ancient light as it travels. By the time it reaches our telescopes, the wavelengths have been pulled longer, shifted toward the red end of the spectrum. It's like the universe is painting its own history in colors that tell us how far away and how long ago these distant objects existed. But there's a limit to how far back we can see. Not because our instruments aren't powerful enough, though that's part of it. The real boundary comes from the fundamental properties of light and time themselves. There was a moment, early in cosmic history, before which light couldn't travel freely through space. This creates what we might call an invisible horizon. Beyond that point, no matter how advanced our technology becomes, we simply cannot observe directly. It's not like running into a wall or reaching the edge of a map. The boundary exists because information itself has only had so much time to cross the vast distances of space. If you imagine traveling toward this cosmic horizon, something strange would happen. Just like walking toward the horizon on Earth. It would always seem to move away from you. The edge isn't a fixed barrier, it's more like a moving bubble of visibility, expanding as the universe ages and light has more time to reach us. This raises a profound question about what exists beyond our observable limits. The space we can't see isn't necessarily different from the space we can. It's probably filled with more galaxies, more stars, more planets. The same physical laws apply there, the same processes of formation and evolution continue. Some theories suggest the universe extends infinitely in all directions. If that's true, then beyond our visible horizon lies an endless continuation of cosmic structure. Other possibilities include a universe that curves back on itself, where traveling far enough in one direction might eventually bring you back to where you started, though the distances involved make this purely theoretical. The human mind struggles with these concepts because we're used to things having clear boundaries. We expect beginnings and endings, edges we can touch or measure. But the universe operates on scales where our everyday intuitions simply don't apply. What we call the edge of the observable universe is really just the edge of our knowledge. It's the furthest point from which information has had time to reach us. Beyond that boundary, reality continues, governed by the same forces, following the same patterns we observe in our local cosmic neighborhood. There's something both humbling and exciting about this limitation. No matter how far our technology advances, there will always be regions of space beyond our direct observation. This isn't a failure of science, it's simply a consequence of living in a universe with finite age and finite speed limits for information. The light we detect today left its source billions of years ago. We're seeing these distant galaxies not as they are now, but as they were in the ancient past. Meanwhile, those same galaxies have continued evolving, changing, perhaps even dying, while their old light was making its way to us. This creates a strange form of cosmic archaeology. Every observation is a glimpse into history, a fossil record written in electromagnetic radiation. The deeper we look into space, the further back in time we see, until we approach that fundamental limit, where the universe becomes opaque to our instruments. Scientists continue pushing against these boundaries, developing new ways to extract information from the faintest signals. Each improvement in detector sensitivity, each advance in analysis techniques, allows us to peer slightly further into the cosmic past, but the horizon will always remain, marking the limits of what can be directly observed. Perhaps there's something appropriate about this permanent mystery, at the edges of our knowledge. The universe doesn't reveal all its secrets at once. It maintains a sense of scale and wonder that keeps us curious, keeps us searching, keeps us humble about our place in the vast cosmic story that continues far beyond what we can see. The night sky presents us with an illusion of stillness. When we gaze upward, stars seem locked in place, constellations holding their ancient patterns. Our ancestors relied on this apparent steadiness, using stellar positions to navigate oceans, time their harvests, weave their stories. Yet beneath this cosmic calm lies a truth that took humanity centuries to uncover. Everything above us moves. The universe itself stretches, carries galaxies along like leaves on an expanding river. This motion happens so gradually, so vastly, that human eyes cannot detect it within a single lifetime. We see snapshots of eternity, missing the grand choreography unfolding around us. Space expansion differs completely from any movement we know on Earth. Galaxies don't rocket through empty void like sparks from a campfire. Instead, the fabric of space itself grows larger, pulling distant objects apart. Think of it as cosmic inflation happening everywhere at once, in all directions without pause. Early 20th century astronomers first noticed something peculiar in starlight. Light from distant galaxies appeared redder than expected. This red shift occurs when light sources move away from observers, stretching light waves to longer, redder wavelengths. The principle mirrors how ambulance sirens sound higher when approaching, lower when retreating. Edwin Hubble gathered these observations, discovered a remarkable pattern. More distant galaxies showed greater red shift. The farther away a galaxy sat, the faster it retreated from us. This wasn't random, cosmic motion, but systematic expansion happening uniformly throughout space. Picture dots drawn on a balloon's surface. As the balloon inflates, every dot moves away from every other dot. Dots farther apart, separate faster than nearby ones. No single dot occupies the center. Each shares the same expanding perspective. Our universe works similarly. From any vantage point, expansion appears identical. No location holds special privilege as the cosmic center. This discovery shattered millennia of assumptions. Humans long believed the universe was static, eternal, simply existing in unchanging vastness. But expansion implied something profound, a beginning. If galaxies now drift apart, they must have once crowded together. Everything we observe today once occupied a smaller, hotter, denser state. This realization birthed the Big Bang concept. Not an explosion in space, but the expansion of space itself from conditions almost beyond imagination. Time, matter, energy, the very dimensions we inhabit, all emerged from this initial moment. Before it, our familiar concepts of before and after lose meaning entirely. Expansion doesn't affect everything equally. Stars don't swell larger. Planets don't drift from their orbits. The forces binding local systems, gravity holding solar systems together, far exceed expansion's gentle pull. Cosmic stretching operates only at the grandest scales, in the vast emptiness between galaxy clusters. Within galaxies, gravity dominates completely. This explains why our Milky Way actually approaches the Andromeda Galaxy. Their mutual gravitational attraction overpowers universal expansion. Billions of years hence, these galaxy neighbors will merge into a single, larger system. Local physics trumps cosmic expansion in this celestial dance. Between galaxy clusters, however, expansion wins decisively. The greater the distance, the more space stretches. Galaxy clusters separate like islands drifting on an ocean of expanding spacetime. What began as a universe where everything was close together has become one where vast emptiness grows ever vaster. Redshift reveals not just motion, but time itself. Light from distant galaxies shows us their past, when they were younger, closer, different. We peer backward through cosmic history with every observation. The universe presents us with its own autobiography, written in wavelengths of ancient light. This expansion raises profound questions about our place in existence. We inhabit a cosmos that grows larger each moment, where distances increase without limit. What seemed permanent and fixed reveals itself as temporary, evolving, headed toward futures we can barely imagine. Perhaps there's something humbling in this realization, that even the vast seems small when viewed against the infinite canvas of expanding space. For decades, researchers faced what seemed like a straightforward question about our expanding cosmos. The Big Bang had set everything in motion, pushing galaxies outward in all directions. But gravity, that fundamental force we know so well from dropping our morning coffee, should work against this expansion. It pulls things together, always. So naturally, scientists expected the universe's growth to gradually slow down over time. The logic felt almost inevitable. If you throw a ball upward, gravity eventually wins, bringing it back down. The same principle should apply to the entire cosmos. Everything that exists, all the matter scattered across space, should create enough gravitational pull to at least slow the expansion. Maybe even stop it completely, maybe even reverse it into a dramatic collapse. This became the defining question of cosmology. Two possible futures stretched before us. In one scenario, the universe would keep expanding forever, growing colder and darker as galaxies drifted apart. In the other, expansion would halt, then reverse, crushing everything back together in what scientists called the Big Crunch. The fate of literally everything depended on a cosmic tug-of-war between outward momentum and inward gravitational pull. Then came observations that changed everything we thought we knew. Teams of astronomers pointed their telescopes at distant exploding stars, using them as cosmic lighthouses to measure how fast galaxies were moving away from us. What they found defied all expectations. The expansion wasn't slowing down at all. It was speeding up. This discovery turned our understanding upside down. Galaxies weren't just moving away from us, they were accelerating as they went. Something was actively pushing them apart, overpowering gravity's attempts to hold things together. That something got a name. Dark energy, though calling it energy might be misleading. It's not like the energy stored in a battery or released by burning wood. It's woven into the very fabric of space itself. Think about it this way. Every cubic meter of empty space contains this mysterious dark energy. As space expands, creating more volume, more dark energy comes into existence. It's like a cosmic inflation that feeds on itself, growing stronger as the universe gets bigger. The more space there is, the more dark energy there is to push things apart even faster. The numbers are staggering when you think about them. Dark energy makes up roughly 70% of everything that exists. Regular matter, the atoms that form stars and planets, and coffee cups, accounts for less than 5%. The rest is dark matter, another mysterious component we can't see directly. This means the universe we experience directly represents just a tiny slice of reality. When astronomers look at those distant supernovas, they're seeing light that traveled for billions of years to reach us. That light carries information about how fast those galaxies were moving when the light first started its journey. By comparing galaxies at different distances, we can trace the history of cosmic expansion, like reading growth rings in an ancient tree. The pattern tells a remarkable story. Early in the universe's history, matter and radiation were dense enough that gravity could slow the expansion significantly. But as space grew and matter spread out, dark energy began to dominate. Around 5 billion years ago, the balance tipped. Expansion started accelerating, and it's been picking up speed ever since. This acceleration has profound implications for what lies beyond our observable horizon. Right now, we can see galaxies that are billions of light years away. Their light has been traveling toward us since the universe was young, but if expansion keeps accelerating, some of these distant galaxies will eventually slip beyond our reach forever. It's not that they'll disappear or be destroyed. They'll still be out there, spinning and forming new stars. But space will be expanding so rapidly between us that their light will never catch up to us again. They'll fade from view, not because they've gone dark, but because the universe has grown too fast for their signals to bridge the gap. This creates a strange and somewhat melancholy picture of cosmic evolution. Future astronomers, working billions of years from now, will look up at a much emptier sky. They'll see fewer galaxies, not because fewer exist, but because most will have been carried beyond the visible horizon. They might never know, just from observations, that our rich, galaxy-filled universe ever existed. We're living in a special time, cosmologically speaking. We can still see the cosmic microwave background, that faint afterglow from when the universe first became transparent to light. We can observe distant galaxies in various stages of evolution. We can piece together the story of how simple hydrogen and helium gas eventually formed the first stars, which forged heavier elements and died in spectacular explosions that seeded space with the ingredients for planets and life. The expansion isn't uniform everywhere, though. Gravity still wins on smaller scales. Our Milky Way galaxy hangs together just fine. In fact, it's gravitationally bound to the nearby Andromeda galaxy, and they're actually approaching each other, destined for a collision in about 4 billion years. The local group, our small collection of galaxies, will likely merge into a single, massive galaxy. But step back far enough, and expansion dominates everything. Galaxy clusters, some of the largest structures in the universe, are being carried apart by the stretching of space itself. It's like watching islands drift apart as the ocean between them grows wider. This cosmic expansion also gives us a way to measure the universe's age. By determining how fast galaxies are moving apart right now, we can calculate backward to find when they were all in the same place. Combined with other observations, this tells us the universe is approximately 13.8 billion years old. That's when space began expanding from an incredibly hot, dense state we call the Big Bang. But measuring this expansion rate has created its own mystery. Different methods give slightly different answers. Teams using nearby supernovas get one number for the expansion rate. Teams analyzing the cosmic microwave background get a different number. The disagreement might seem small, but in cosmology, precision matters enormously. This tension suggests we might be missing something important about how the universe works. Perhaps dark energy isn't constant, but changes over time. Perhaps there are additional forms of matter or energy we haven't discovered yet. Perhaps our understanding of gravity needs refinement on cosmic scales. These uncertainties remind us that the universe still holds secrets. Each answer we find seems to reveal new questions waiting in the wings. The accelerating expansion we've discovered is probably just one piece of a much larger puzzle about the nature of reality itself. The fabric of space itself grows larger, moment by moment, like an invisible tide that carries everything along with it. Scientists puzzle over this phenomenon, constantly refining their understanding piece by piece. When we try to picture cosmic expansion, our minds often conjure images of distant galaxies racing through empty void, like ships sailing across a dark ocean. But this mental picture, while comforting, misses something fundamental about reality. Space doesn't stay still while objects move through it. Instead, the very stage on which cosmic drama unfolds stretches and grows. Imagine two distant galaxies, each one anchored in place, yet drifting apart because the universe itself expands between them. The distance increases, not because either galaxy travels anywhere, but because space creates more of itself. This raises a question that has puzzled curious minds for generations. If the universe expands, what does it expand into? The answer challenges our everyday experience of boundaries and containers. There is no cosmic room, no external void waiting to be filled. The universe resembles the surface of a balloon more than the balloon itself. As that surface stretches, it needs no surrounding space to accommodate its growth. The strangeness deepens when we consider where this expansion centers itself. Logic suggests there should be some cosmic ground zero, some special location from which everything spreads outward. Yet, observations reveal something far more mysterious. Every point in space appears to sit at the center of expansion. From any galaxy, any star, any planet, the view looks identical, everything else retreating in all directions. This peculiar property reshapes how we understand cosmic origins. The Big Bang wasn't an explosion that happened somewhere specific, sending matter flying through pre-existing space. Instead, it marked the beginning of space itself, everywhere simultaneously. Every region claims equal importance. Every observer witnesses the same expanding pattern from their particular vantage point. Consider the philosophical weight of this revelation. In a universe where every location serves as center, no place can claim special cosmic significance. Earth occupies no privileged position, yet neither does anywhere else. We exist in a democracy of cosmic real estate, where significance comes not from location, but from the complex chemistry of life itself. The mathematics behind expansion creates two possible scenarios for cosmic geometry, each more mind-bending than the last. If space extends infinitely in all directions, then expansion means it has always been infinite, simply becoming less dense as it grows. Imagine an infinite grid of points, each one moving away from its neighbors, the grid itself stretching without bounds. Alternatively, the universe might be finite yet unbounded, like the surface of that balloon we considered earlier. An ant walking across such a surface would never encounter an edge, never find a place where the balloon simply stops. The surface has definite area, yet no boundary. As expansion continues, this cosmic surface grows larger, accommodating more space without creating edges or limits. Both possibilities eliminate the notion of cosmic borders, of places where space simply ends. Instead, we inhabit a universe of perpetual growth, carrying galaxies and clusters along like leaves on a flowing river. This growth affects everything, from the largest structures down to the light that travels between them. When ancient starlight journeys across billions of years to reach our telescopes, expansion stretches those photons, shifting their colors toward the red end of the spectrum. This cosmic redshift serves as a timestamp, telling us how much the universe has grown since that light began. Each distant galaxy appears redder than it actually is, painted by the expansion of space itself. The elements in our bodies carry signatures of this cosmic growth. Carbon atoms in our cells, oxygen in our blood, iron in our red blood cells, all formed inside dying stars long ago. When those stars exploded, they scattered heavy elements across space, seeding future generations of star formation. Expansion provided the room for this cosmic recycling to operate on vast scales. Without expansion, the universe might have remained a dense hot soup, too cramped for complex chemistry to develop. Stars might never have formed distinct populations, never had the chance to cook heavy elements in their nuclear furnaces. The cosmic story would have unfolded very differently, perhaps never reaching the complexity required for planets, oceans, or life. This connection between expansion and complexity suggests something profound about cosmic evolution. The growing universe doesn't just create more space, it creates more possibilities. Each new region of space represents potential homes for future stars, planets, and perhaps even other forms of consciousness we cannot yet imagine. The boundary of what we can observe, our cosmic horizon, exists because of expansion combined with the finite speed of light. There are galaxies so distant that their light hasn't had time to reach us since the universe began. As time passes, light from more distant objects arrives, gradually expanding our observable domain. Yet, expansion ensures that some regions will forever remain beyond our view. This creates a shifting boundary, not fixed like the edge of a continent, but dynamic like the horizon seen from a ship at sea. As our cosmic vessel sails forward through time, new territory comes into view while other regions slip beyond the edge of what expansion allows us to see. The boundary retreats continuously, always carrying fresh mysteries just beyond our reach. In this expanding cosmos, the question of what lies beyond takes on deeper meaning. There is always more space, more galaxies, more stories written in starlight. The universe grows not just in size, but in complexity, creating new chapters in cosmic evolution that we may never read, hosting dramas that will unfold in regions forever hidden from our instruments. The universe holds mysteries that stretch far beyond what our eyes can see, and understanding these limits reveals something profound about our place in existence. When we gaze into the night sky, we're not just looking across space, we're peering backward through time itself, witnessing light that began its journey millions, even billions of years ago. Picture yourself standing at the edge of an enormous lake on a foggy morning. You can see the water extending outward, but eventually the mist becomes so thick that your vision simply stops. The lake continues beyond that point. You know this, but you cannot witness what lies there. Our universe presents us with a similar boundary, though this one isn't made of fog or water, but of time and the fundamental speed at which light travels. This cosmic boundary exists because light, despite being the fastest thing we know, still takes time to cross the vast emptiness between stars and galaxies. Since our universe began expanding roughly 13.8 billion years ago, you might assume we can see objects that are 13.8 billion light-years away. But the reality proves far more complex and fascinating. While ancient light traveled toward us across billions of years, space itself continued expanding, stretching like a balloon being slowly inflated. This expansion carried those distant light sources even further away. So today, the most distant objects we can observe sit approximately 46 billion light-years from Earth. The sphere of space we can potentially see spans about 93 billion light-years from edge to edge, an almost incomprehensible volume containing hundreds of billions of galaxies. Each of these galaxies holds billions of stars, and around those stars, countless worlds might harbor forms of life we can barely imagine. The philosophical weight of this vastness can make you pause, can make you wonder about the nature of existence itself, when our entire observable reality represents just a small bubble within something potentially infinite. But here's where the story takes an unexpected turn. This boundary of visibility isn't fixed like the walls of a room. Billions of years ago, our ancestors, had they possessed telescopes, would have seen a smaller universe, one with fewer visible galaxies and stars. The cosmic horizon was closer then, because light from more distant regions hadn't yet had time to reach Earth. You might expect that billions of years from now, we'll see even more of the universe as light from increasingly distant regions finally arrives. In some cases, this will happen. New galaxies will indeed appear at the edge of our vision as their ancient light finally completes its long journey to us. However, something strange and almost melancholy occurs due to a mysterious force scientists call dark energy. This force drives the expansion of space to accelerate, meaning the universe grows larger at an ever-increasing rate. This acceleration creates a peculiar situation where many galaxies visible today will eventually disappear from our view forever. Imagine watching a friend walk away from you, but instead of moving at a steady pace, they walk faster and faster until they vanish beyond a hill. Similarly, galaxies near the edge of our current vision will be carried away by expanding space until their light can no longer bridge the growing gap between us. They'll continue to exist, continue to shine, continue their cosmic dance, but for us, they'll fade into permanent invisibility. At the same time, regions of space currently beyond our horizon may never become visible, no matter how many billions of years pass. The expansion of space occurs faster than light can cross the increasing distance, creating an ultimate limit to what we can ever hope to observe. Consider a galaxy sitting just at the edge of what we can detect today. Its light reaches us faint and stretched, shifted into infrared wavelengths by the expansion of space. Advanced telescopes designed to capture this stretched light can still reveal these distant worlds to us. But given enough time, that same galaxy will slip beyond our reach as space grows between us too rapidly for its light to complete the journey. This represents more than just an observational challenge. It touches on fundamental questions about knowledge itself, about the boundaries of what any intelligence, no matter how advanced, can ever hope to understand about reality. The cosmic horizon carries another meaning as well. one that takes us back to the very beginning of everything we know. Beyond the most distant galaxies lies something even more ancient, the afterglow of creation itself. When our universe was approximately 380,000 years old, it had cooled enough for the first atoms to form. Before this moment, space was filled with a hot soup of particles that scattered light in every direction, making the universe opaque, like trying to see through thick fog. But once atoms formed, light could suddenly travel freely through space for the first time. The universe became transparent, and this first light has been journeying through space ever since. Today, after more than 13 billion years of travel, this primordial light reaches us as faint microwave radiation spread evenly across the entire sky. Scientists call this the cosmic microwave background, and it represents the oldest light we can ever hope to detect with conventional methods. This background radiation forms another kind of horizon, not a boundary in space, but a boundary in time. We cannot see beyond this wall of light to witness the universe's first moment directly, because before atoms formed, the cosmos was simply opaque to the kind of radiation our instruments can detect. When researchers map this ancient radiation, they discover it isn't perfectly uniform. Tiny temperature variations, smaller than 1,000th of a degree, reveal the seeds from which all galaxies, stars, and planets would eventually grow. These minute fluctuations in the cosmic microwave background provide us with what amounts to a baby picture of the universe, showing us the cosmos when it was just a tiny fraction of its current age. There's something deeply moving about realizing that this faint glow surrounding us in all directions connects us directly to the birth of everything we know. Every atom in your body, every molecule of air you breathe, every element that makes up the earth and stars, all of it traces back to that ancient moment when the universe first became transparent. The cosmic microwave background reminds us that we exist within a story much larger and older than human civilization, larger than our planet, larger than our sun. We are quite literally made of processed starlight, assembled from elements forged in the hearts of ancient stars that lived and died billions of years before our solar system even existed. This realization places our daily concerns in a fascinating perspective. While we worry about deadlines and relationships and the thousand small dramas of human life, we're simultaneously riding on a small world through an expanding universe filled with wonders beyond imagination, surrounded by the gentle glow of creation itself. The universe keeps its earliest secrets locked away, wrapped in a veil of ancient heat and density. When we peer into space, we're also peering backward through time itself. Every photon that reaches our eyes carries news from the past, some from billions of years ago. This cosmic boundary isn't just about distance, it's about time. Light can only travel so fast, and the universe has only existed for so long. Put these two facts together, and you get a natural limit to what we can observe. Beyond this limit, the universe simply hasn't had enough time to send us its light. For thousands of years, people wondered how big the cosmos really was. Ancient civilizations imagined crystal spheres holding up the stars. Others thought the heavens ended just beyond what they could see with their naked eyes. Now we know better, but in some ways we've discovered an even stranger truth. The observable universe extends roughly 46 billion light-years in every direction. That might sound like a contradiction at first. After all, the universe is only about 14 billion years old. How can we see light from something 46 billion years away? The answer lies in expansion. While light was traveling toward us, space itself was stretching, carrying those distant sources even farther away. Think of it like watching a friend walk away from you while you're both standing on a moving walkway that's speeding up. Your friend appears to move much farther than their steps alone would carry them. Space works similarly, expanding and carrying galaxies along with it. This creates something philosophers and scientists call the cosmic horizon. It's not a wall you could touch or a barrier made of matter. It's more like the edge of a shadow cast by time itself. Beyond this horizon, there are almost certainly more galaxies, more stars, more worlds. But their light will never reach us, no matter how long we wait. The horizon moves, but not in the way you might expect. As the universe ages, Light from slightly more distant objects has time to reach us, so the observable universe slowly grows larger. But it also shrinks in another sense, because expansion carries distant galaxies away faster than new light can arrive from even farther out. Every observer in the universe sits at the center of their own cosmic bubble. An alien on a planet in the Andromeda Galaxy would see a different slice of the universe than we do. Their horizon would overlap with ours, but it wouldn't be identical. Some galaxies visible to them would be forever hidden from us, and vice versa. This creates a humbling picture. The universe becomes like a vast jigsaw puzzle, where no single observer can ever see all the pieces. Each viewpoint reveals something unique, something that complements but never completes the picture. Earthly horizons work differently. When you stand on a beach and look out at the ocean, you're seeing the limit of your line of sight. Climb a tall building and you can see farther. Fly in a plane and the horizon expands even more. But the cosmic horizon can't be overcome by changing your position or building better telescopes. It's built into the very structure of space-time. Scientists sometimes describe this boundary as the surface of last scattering. It marks the moment when the universe cooled enough for atoms to form and light to travel freely through space. Before that moment, the cosmos was opaque, filled with a hot plasma that absorbed and scattered photons. This wall of ancient light surrounds us in every direction. The cosmic microwave background radiation comes from this surface. It's the afterglow of creation itself, stretched and cooled by billions of years of expansion. When radio telescopes detect this faint signal, they're seeing the universe as it was when it first became transparent, roughly 380,000 years after the Big Bang. Beyond this ancient boundary, the universe was dark in a way we can barely imagine. Not dark because there was no light, but dark because light couldn't travel. Photons would scatter off free electrons almost immediately, creating a cosmic fog thicker than anything we experience on Earth. The horizon also raises questions about what lies beyond our view. The most straightforward answer is more of the same. More galaxies distributed through expanding space, following the same physical laws we observe in our local region. But there could be surprises too, structures or phenomena that exist on scales larger than our observable universe. Some theories suggest the cosmos might be infinite, stretching on forever in all directions. Others propose it might curve back on itself like the surface of a sphere. If you could somehow travel far enough in a straight line, you might eventually return to your starting point. These ideas remain largely untestable, since they depend on regions we can never observe. The horizon separates us from more than just empty space. If other civilizations exist beyond our cosmic boundary, they will remain forever unknown to us. Their signals can never reach us, and ours can never reach them. This isn't a limitation of our technology, it's a fundamental feature of the universe itself. In some ways, this creates the ultimate form of cosmic loneliness. There could be countless worlds out there, teeming with life and intelligence, but they exist in a realm we can never access. They might have solved problems that puzzle us, created art that would move us, or discovered truths about the universe that remain hidden from our view. But there's also something oddly comforting about the cosmic horizon. It guarantees that the universe will always hold mysteries. No matter how much we learn, how far our knowledge advances, there will always be more to discover. The boundary of our vision creates a kind of eternal frontier. This differs from other scientific limits in important ways. We might someday develop technologies that let us see individual atoms or detect gravitational waves from the first moments after the Big Bang. But the cosmic horizon is different. It's not a challenge to be overcome, but a fundamental feature of reality itself. The existence of this boundary tells us something profound about the nature of the cosmos. It has a history, a beginning, a finite age. Without these properties, there would be no horizon at all. Light from arbitrarily distant sources would have had infinite time to reach us, and we would see an infinite universe stretching in all directions. Instead, we inhabit a cosmos that reveals itself gradually, layer by layer, like an onion being peeled back by time itself. Each moment that passes brings light from slightly more distant sources, but also carries other sources farther away. The universe ages and expands around us, creating an ever-changing but never complete picture. This perspective transforms how we think about our place in existence. We're not just observers looking out at a static cosmos, we're participants in an unfolding story. The light, reaching our eyes tonight, left distant stars and galaxies at specific moments in cosmic history. We're seeing the universe not as it is, but as it was. The cosmic horizon reminds us that knowledge itself has limits, not because of our failings, but because of the fundamental structure of reality. There will always be questions we cannot answer, places we cannot go, things we cannot see. And perhaps that's exactly as it should be. There's something profound about recognizing that our understanding will always have edges, places where certainty fades into the unknown. This recognition doesn't discourage exploration, it fuels it. The boundary between what we know and what remains hidden acts as a constant invitation to build more sensitive instruments, to ask deeper questions, to remain modest about our position in something so immeasurably vast. The concept of limits isn't just a scientific reality, it carries philosophical weight too. Our knowledge has boundaries not because we lack dedication or precision, but because reality itself is constructed this way. We exist within confines we simply cannot transcend. Yet these very confines point towards something that extends beyond them. There's an interesting contradiction here. The fact that we cannot perceive what lies beyond certain thresholds makes us absolutely certain that something does lie beyond. What conceals also reveals, in its own mysterious way. When you glance up at the night sky, you're witnessing the conclusion of journeys that began incredibly long ago. Each pinpoint of light represents not what a star looks like now, but what it looked like in the past. The sparkle that enters your vision tonight might have started its voyage before humans had even appeared on Earth. Consider Proxima Centauri, our nearest stellar neighbor, after the Sun. Its light requires just over 4 years to reach us, which means observing it is like peering 4 years backward through time. This distance seems modest when measured against cosmic scales, but it illustrates something fundamental about perception in the universe. Nothing we see is happening right now. Every image arrives delayed, carrying information from some earlier moment. Push this concept further, and it becomes even more remarkable. The light streaming from the Andromeda Galaxy is more than 2 million years old. When those photons began their journey, Earth was populated not by modern humans, but by early ancestors who hadn't yet developed the tools and languages we consider basic today. While these ancient relatives were crafting stone implements, or moving through landscapes completely untouched by civilization, light was already traveling through space, photon by photon, eventually arriving at your eyes tonight. Each time you observe that galaxy, you're establishing a connection with beings who existed countless generations before you were born. Now imagine extending this backward glance even further. The most distant galaxies detectable by our most powerful telescopes are so far away that their light has been traveling for more than 13 billion years. The radiation entering instruments like the James Webb Space Telescope tonight first escaped when the universe was only a few 100 million years old. Stars were just beginning to ignite, galaxies were smaller and more chaotic. And the organized structures we observe today existed only as clouds and loose clumps of matter. Those primordial flashes of light have continued traveling undisturbed until we developed the technology to capture them. In this way, astronomy becomes less about looking outward through space and more about looking backward through time. Every observation functions as a time machine, revealing not what existed then, but what existed then. The journey of light involves more than simple distance. It's shaped by everything it encounters along the way. Craphage braking. Space appears mostly empty, but it's not completely vacant. Photons pass through gas clouds, dust fields, and the gravitational influence of massive objects. These encounters modify their path in measurable ways. Gravity itself can bend light, creating what scientists call gravitational lensing. When light from a distant galaxy passes near a massive cluster of matter, its trajectory curves, and we see the galaxy's image stretched or amplified. Light's journey isn't always straight. It gets bent and twisted by the massive intervening objects. For astronomers, this isn't an obstacle. It's actually a valuable tool. The bending reveals the presence of matter that might otherwise remain undetected. Some of this matter is visible to us directly. Some of it consists of dark matter, invisible to normal observation, but revealed by how it influences light during its long voyage. Dust plays its own role too. Within galaxies, dust clouds scatter and absorb specific wavelengths, making stars appear redder or dimmer than they actually are. To compensate for this effect, astronomers must carefully calculate how light has been filtered during its passage. What finally arrives at our telescopes isn't exactly what was originally emitted. It's a record that has been altered by billions of years of interactions. Reconstructing the original signal requires detailed analysis, but the effort reveals not only information about the distant source, but also about the intervening space itself. Light serves as both messenger and map, carrying information about everything it has encountered. One of the most striking aspects of light's cosmic journey involves how the expansion of space affects it. As space itself stretches, the wavelength of light traveling through it stretches too. Radiation that began as ultraviolet or visible light can arrive at our instruments as infrared or even radio waves, shifted toward longer wavelengths by the expansion that has occurred during its transit. When we think about the universe stretching out around us, there's something almost magical happening with every beam of light that reaches our eyes. The expansion of space itself acts like a cosmic conveyor belt, pulling galaxies away from each other at speeds that grow faster with distance. This expansion doesn't just move objects, it actually stretches the light waves as they travel, like pulling on a spring. A photon that started its journey as brilliant visible light from some distant star can arrive at Earth billions of years later as a gentle infrared whisper or even a faint microwave signal. The universe has literally stretched that light, cooling it down during its endless voyage. This stretching tells us stories, because the more stretched the light appears, the further back in time we're actually looking. There's something beautifully tragic about this cosmic dance. Right now, there are galaxies whose light is just reaching us, their ancient glow finally completing a journey that began when the universe was young. But here's the catch: because space is expanding at an accelerating rate, those same galaxies are already racing away from us, faster than any new light could ever hope to catch up. The light we're seeing right now, it's the last message we'll ever receive from them. After this final glimpse, they'll fade beyond our horizon forever, slipping into a darkness we can never penetrate again. Think about what this means for the nature of observation itself. Every photon carries with it a timestamp from the ancient past. That speck of light hitting your eye tonight might have begun its journey when Earth was still a molten ball of rock. During that photon's travels, entire evolutionary trees have grown and died. Continents have wandered across the planet's surface. Ice ages have carved valleys and melted away, and countless civilizations we'll never know about have risen and fallen to dust. The photon doesn't know about any of this, of course. It just keeps moving in a straight line through space, patient and undistracted, until it finally reaches a telescope mirror or your retina and gets absorbed. That moment when it arrives, its epic journey ends forever, and its story becomes part of our knowledge. Every second, billions of these ancient travelers arrive from all directions, each one carrying information encoded in its wavelength and intensity. This is why astronomy is really archaeology, but instead of digging down through layers of Earth, we're collecting the fossilized light of the past. Not all light makes it to us the same way, though. Earth's atmosphere acts like a selective filter, blocking some wavelengths while letting others pass through easily. Gamma rays and X-rays, with their short, energetic wavelengths, get stopped by our protective atmospheric blanket. That's why telescopes designed to see these high-energy signals have to float in space, above the air that shields us from radiation. Radio waves, on the other hand, slide through our atmosphere, like it's barely there, which is why radio astronomy can happen from the ground. Each type of light reveals different secrets about the cosmos. Radio wavelengths show us cold gas clouds drifting between the stars. Infrared light penetrates dust clouds to reveal the warm nurseries where new stars are being born. X-rays expose the superheated gas swirling around black holes, matter so hot it glows with deadly energy. When you combine all these different windows, you start to see the universe as it really is, not just as our eyes evolve to perceive it. Every wavelength tells part of the story, and together they create something like a cosmic symphony, with each instrument contributing its own voice to the larger composition. There's something profound about realizing that light has been our guide to the cosmos since long before we had any instruments at all. Our ancestors looked up at the night sky with nothing but their eyes, and those same photons that had traveled across impossible distances would complete their journeys by striking the molecules in human retinas, triggering electrical signals that became the experience of seeing starlight. Modern telescopes work on exactly the same principle, just extended into ranges our biology never equipped us to detect. But whether it's your eye or a billion-dollar space telescope, the process depends entirely on light completing its patient journey across space and time. Light moves faster than anything else in the universe, racing along at about 300,000 kilometers every second. At that speed, you might think nothing could take very long to reach us, but the cosmos is so vast that even light at its incredible velocity needs eons to cross the larger distances we're talking about. A beam from your flashlight takes just over a second to reach the moon. A radio signal to Mars might take anywhere from 4 to 20 minutes, depending on where the planets happen to be in their orbits. To reach Pluto takes several hours, but for light to cross from one side of our own galaxy to the other requires about 100,000 years of continuous travel. And from the most distant galaxies we can observe, light has been traveling for billions of years. This is what astronomers mean when they talk about look-back time. When we see a galaxy with a look-back time of 10 billion years, we're seeing it exactly as it was 10 billion years ago, not as it exists today. For some of the most distant objects, the gap between then and now is so enormous that what we're looking at may no longer exist in anything like the same form. Stars that were burning brightly when that light began its journey may have long since exploded or faded to cold embers. Entire galactic structures may have been torn apart by gravitational forces or swallowed by black holes. But the image remains perfectly preserved in the light that's still making its way toward us. Like a photograph frozen in amber, the light from these distant sources doesn't arrive as a flood either. By the time those ancient photons reach Earth, they're spread incredibly thin across the vast distances they've traveled. Telescopes have to gather them patiently, sometimes collecting for hours or even days to build up enough signal for a single image. Those famous deep field photographs, the ones that show thousands of galaxies in what looks like an empty patch of sky, were created by pointing a telescope into apparent nothingness and leaving the shutter open for days at a time. Gradually, enough photons accumulated to reveal entire cosmic cities of stars, each one a faint speck representing light that had been journeying across space for most of the universe's history. There's something almost meditative about this process, the way it mirrors our own search for understanding. Knowledge doesn't come quickly or easily. It requires patience, careful observation, and the willingness to wait for truth to emerge slowly from the darkness. Each photon that finally reaches us carries far more than just brightness too. Encoded in its wavelength and intensity is information about its source, the temperature of the star that created it, the chemical elements that were present, the speed at which its home galaxy is moving. By splitting light into its component colors, astronomers can read these details like lines of text in an ancient language. Right now, as you're sitting wherever you are, you're surrounded by this invisible rain of cosmic messengers. Even if you're indoors, light from distant stars is still reaching Earth's atmosphere, bouncing around, filtering through windows and walls in tiny amounts. Some of the photons that will strike the ground outside tonight began their journeys before our solar system even formed, completing their odyssey by arriving at a planet that only recently developed life forms capable of noticing them. The patience involved is almost incomprehensible when you really think about it. These particles of light have been traveling faithfully across space for longer than complex life has existed on Earth, carrying their cargo of information through the expanding cosmos. past countless other worlds and civilizations we'll never know about, until they finally reach the one planet we know of, where conscious beings have evolved the ability to catch them and decode their messages. In a way, asking what lies on the other side of the universe is really asking about the nature of light's journey itself. Without those traveling photons, there would be no edge for us to contemplate, no horizon to measure, no expansion to trace through time. The entire story of where we are and what surrounds us comes to us through these tiny witnesses to cosmic history, each one carrying a piece of the puzzle that helps us understand our place in the larger scheme of things. Light travels at an incredible speed, yet it still needs time to journey across the cosmic distances. This simple fact creates one of the most profound boundaries in existence. The universe began roughly 13.8 billion years ago, which means light has only had that long to reach us from the most distant places. Think of it this way: when you look up at the night sky, you're seeing a museum of cosmic history. Each star shows you light that left its surface years, decades, or even centuries ago. The farther away something is, the older the light becomes by the time it reaches your eyes. This creates what scientists call the observable universe, a sphere around Earth that contains everything we can possibly see. It's like standing in the middle of a vast library where you can only read the books within arm's reach. Beyond that circle, there are more books, countless more, but they remain forever out of your grasp. The edge of this observable sphere isn't a wall or a barrier made of matter. It's simply the point where light hasn't had enough time to complete its journey to us. Beyond this boundary lies the unobservable universe, regions that are absolutely real but completely hidden from our view. Here's where things get truly mind-bending. If you could somehow teleport yourself to a galaxy far beyond our observable boundary, you wouldn't find yourself at the edge of existence. Instead, you discover a perfectly normal region of space, filled with stars, gas clouds, and possibly even planets with their own stories unfolding. From that distant vantage point, you'd have your own observable universe, a sphere of visibility centered around your new location. What's invisible to us would be perfectly visible to you. What we can see clearly would be beyond your horizon. Each point in the universe has its own sphere of what it can observe. This concept challenges our most basic assumptions about reality. We naturally assume that what we cannot detect might not exist at all. Our daily experience teaches us to trust our senses, to believe in what we can see and touch. But the universe operates on principles that extend far beyond human perception. Consider infrared radiation, completely invisible to our eyes, yet constantly surrounding us. We've built instruments to detect it, and now we know it carries crucial information about temperature and heat. Ultrasonic frequencies exist well above our hearing range, yet entire species navigate their world using these sounds. The same principle applies to cosmic scales. The unobservable universe isn't a theoretical construct or a mathematical curiosity. It's simply the part of reality that exists beyond our instrumental reach, no less real than the ground beneath your feet, just impossibly distant. This limitation affects how we understand the universe's overall structure. When cosmologists study space, they're working with an incomplete picture. The observable portion appears flat and remarkably uniform, looking roughly the same in every direction we examine. But what lies beyond our horizon could tell a completely different story. Space might curve back on itself in ways we cannot detect. There could be regions where matter behaves differently, where the fundamental constants of physics take on other values, where the very rules of reality follow different patterns. The observable universe already contains numbers that stretch human comprehension to its breaking point. Its radius extends about 46 billion light-years in every direction. Within this sphere, hundreds of billions of galaxies drift through the cosmic darkness. Each galaxy houses hundreds of billions of individual stars. Around those stars, countless planets orbit in endless variety. When you multiply these astronomical numbers together, the total becomes almost meaningless in human terms. And yet, this incomprehensible vastness represents only the portion we can actually observe. The unobservable universe could extend much farther, perhaps infinitely, in all directions. If the universe truly has no edge, then everything we can see, every galaxy in our most powerful telescopes, every distant quasar and nebula, amounts to something like a single drop in an endless ocean. The scale becomes so large that it defies not just imagination, but almost defies meaning itself. Picture yourself standing in a dense forest on a foggy morning. The mist limits your vision to perhaps 50 feet in any direction. You can see the trees clearly within that circle, but you know with certainty that the forest continues beyond the fog. More trees stand just outside your view, and more beyond those, stretching far past where your eyes can reach. The universe works exactly like this forest. The fog isn't made of water droplets suspended in air, but of time itself and the expansion of space. Our vision is limited not by mist, but by the finite age of the cosmos and the maximum distance light can travel within that time frame. This boundary represents something unique in human experience. Most limitations we encounter can be overcome with better tools, more time, or different approaches. But the edge of the observable universe is set by the fundamental structure of reality itself. No telescope will ever be powerful enough to see beyond it, because the light from those regions simply hasn't had time to begin its journey toward us. In some distant regions, space itself expands faster than light can travel through it. This means certain galaxies are moving away from us so quickly that their light can never bridge the growing gap between us. They exist in a realm that is permanently separated from our view, not by choice or limitation of technology, but by the basic laws that govern how the universe operates. Beyond the edges of what we can see, the universe keeps going. Scientists think there might be regions out there that look a lot like our own neighborhood. Galaxies spinning in the darkness, stars burning bright, maybe even life taking hold on distant worlds. If space really goes on forever, then something remarkable becomes possible. The mathematics of infinity suggests that patterns repeat. Somewhere out there, in the vast unobservable regions, matter might arrange itself in exactly the same way it did here. Another Earth could exist, with another version of you, living a life almost identical to yours, but with tiny differences. This isn't the stuff of fantasy novels, it's what happens when you apply math to endless space. The catch is, we can never prove it. These regions remain forever, beyond our reach, locked away by the fundamental limits of light and time. The early universe went through something called inflation. In those first tiny fractions of a second, after everything began, space expanded faster than we can imagine. This explains why the cosmos looks so smooth when we peer out in all directions. The cosmic microwave background, that ancient glow from when the universe first became transparent, shows us this uniformity. But inflation also tells us something humbling. What we observe is just a small patch of something much bigger. Imagine looking through a single window in an enormous building and trying to understand the entire structure. That's our situation with the observable universe. This creates a fascinating tension between what we know and what we don't. On one side, we can map our visible cosmos in incredible detail. We know where galaxies cluster, how they move, what they're made of. On the other side, we have to accept that most of reality is hidden from us. Our instruments, no matter how sophisticated they become, can't break through these barriers. Even if we built perfect telescopes, even if we waited billions of years, some regions would stay unreachable. The unobservable isn't just temporarily dark, it's permanently beyond us. Yet this doesn't make studying the universe pointless. By examining what we can see, we learn about what we can't. The distribution of galaxies in our region tells us about structures that probably exist elsewhere. The cosmic microwave background reveals conditions that extend far beyond our view. The unobservable leaves fingerprints on the observable. Its gravity influences the galaxies we can detect. Its presence shapes the patterns we measure. In this way, the invisible makes itself known through its effects on the visible. This raises deep questions about existence itself. If something can never be observed, does it really exist? Scientists say yes, because the laws of physics that work here should work everywhere. There's no reason to think they suddenly stop at the edge of our vision. The universe continues beyond the fog, just like a forest continues past what you can see on a misty morning. The boundary between what we can observe and what we can't isn't sharp or fixed. Right at the edge, there are galaxies whose light barely reaches us, stretched thin by cosmic expansion. Some of these galaxies are probably crossing over into the unobservable right now. The light we're seeing might be the last we'll ever detect from them. This boundary moves constantly. As the universe expands, more galaxies slip away from us. What we can see today might become invisible tomorrow, at least on cosmic timescales. The line between the observable and unobservable shifts, like a tide, always changing. Future astronomers will live under different skies. Billions of years from now, most distant galaxies will have vanished from view. Only our local group of galaxies, held together by gravity, will remain visible. Those future observers might look up and think the universe is small and empty. They might not realize that beyond their horizon lies a vastness filled with hidden galaxies. We live in a special time. The observable universe is still wide and full of light from distant places. This is a privilege of timing, a cosmic coincidence that lets us see far into space and deep into time. The contrast between the observable and unobservable reminds us of our limits. Humans take pride in progress, in building tools that extend our senses. But the universe humbles us by showing that no matter how advanced we become, some truths will always remain out of reach. There's something almost comforting in this limitation. The unobservable reminds us that the cosmos is bigger than our worries, bigger than our problems, bigger even than our entire species. It gives us perspective on our place in the grand scheme of things. We're connected not just to what we can see, but to what we can't. The unseen regions of space will never touch us directly, but they're part of the same reality we inhabit. Our small lives play out against this infinite backdrop. The difference between observable and unobservable isn't a difference in reality, it's a difference in access. One part we can measure and study, the other part we cannot. Both are equally real, equally part of the same cosmos. The line between them exists because of where and when we happen to find ourselves, move to another position in space and time, and the boundary shifts. But there will always be a boundary. There will always be a horizon, separating what we can reach from what we cannot. When we wonder what lies on the other side of the universe, we're really asking about these unobservable regions. The answer is simple. It's still the universe, still real, still following the same physical laws. We may never see it, but we know it continues. The distinction isn't between something and nothing. It's between the seen and the unseen. And in that gap lies both mystery and meaning. A gentle reminder that while knowledge has boundaries, existence itself does not. The question of boundaries seems hardwired into our minds. We live in a world where everything has edges, where every path eventually stops somewhere. Your neighborhood has limits, your country has borders, even the ocean meets the shore. So when we look up at the night sky, it feels natural to wonder, where does it all stop? Our brains struggle with the concept of infinity, because we never encounter it directly. You can count your fingers, measure your room, walk to the end of your street, but infinity, that's something else, entirely. It exists in mathematics in theory, but not in the everyday world we touch and see. Yet when astronomers point their telescopes outward, they find something remarkable. No matter which direction they look, galaxies appear. Not just a few, but countless numbers of them, scattered across space like distant cities. Behind the bright ones, fainter galaxies emerge. Behind those, even dimmer ones wait to be discovered. This pattern doesn't seem to thin out anywhere. The northern sky looks much like the southern sky when you average everything out. The eastern horizon mirrors the western one. There's no hint that one direction leads toward an edge, while another leads toward the center. This uniformity suggests something profound about the nature of space itself. The cosmic microwave background, that ancient light from the early universe, tells a similar story. It appears remarkably smooth across the entire sky. Small variations exist, tiny ripples that would later grow into galaxies, but the overall picture shows no preferred direction, no sign of approaching a boundary. This evidence points toward two fascinating possibilities. The first is that space simply goes on forever. Infinite galaxies, infinite stars, infinite planets, stretching outward without end. It's a concept that can make your head spin, but mathematically it works perfectly well. If the universe is geometrically flat, as current measurements suggest, then infinity becomes not just possible, but likely. Picture a vast sheet of paper extending in all directions, never curling back on itself, never reaching an edge. That flatness could mean that space itself has no limits, but infinity brings strange consequences. In an infinite universe, every possible arrangement of matter must eventually occur somewhere. The laws of probability demand it. Given enough space, enough time, enough random combinations, everything that can happen will happen. That means somewhere out there, another galaxy might look almost exactly like ours. Another star system might mirror our solar system, down to the smallest details. Another planet might host life forms remarkably similar to what we see on Earth. The mathematics goes further. In true infinity, not only would such duplicate exist, they would exist countless times over. An infinite number of near copies, each slightly different, scattered throughout the cosmic expanse. It's a dizzying thought, one that challenges our sense of uniqueness. Yet there's another possibility equally strange. The universe might be finite, but without boundaries. This concept requires a mental leap, but it's easier to understand through analogy. Consider an ant walking on the surface of a basketball. The ant can walk in any direction for as long as it wants. It will never find an edge, never fall off, never encounter a wall. Yet the surface area of that basketball is definitely finite, measurable, limited. Space itself might work the same way. Three-dimensional space could curve back on itself in ways that are difficult to visualize. You could travel in what feels like a straight line for billions of years, only to eventually return to your starting point. In such a universe, light from distant galaxies might take the long way around, creating multiple images of the same objects in different parts of the sky. Astronomers have looked for such repetitions, searching the cosmic microwave background for telltale patterns, but they haven't found any yet. That doesn't rule out the possibility, though. If space curves back on itself, but the curve is enormous, far larger than our observable universe, we wouldn't be able to detect it. We'd be like ants on a sphere, so vast that the surface appears perfectly flat. Our observable universe spans about 93 billion light-years across. That sounds enormous, and it is by any human standard, but it might be just a tiny sample of something much larger. We're trying to determine the shape of an ocean by examining a single drop of water. Current evidence leans toward infinity, toward a universe that simply goes on, without end. The geometry appears flat, the distribution of galaxies appears uniform, and there's no sign of curvature or boundaries anywhere we look, but evidence isn't proof. The tools we use can only see so far, measure so much, detect patterns of limited size. Beyond our horizon lies the unknown, a realm we can theorize about, but never directly observe. This uncertainty isn't a failure of science, it's simply the nature of reality. Some questions push against the very limits of what can be known. We can build models, make predictions, gather data, but the ultimate answer might forever remain just out of reach. Time adds another layer to this puzzle. Even if space goes on forever, the universe isn't static. It's expanding, accelerating, carrying galaxies away from each other at ever-increasing speeds. What we can see today might not be visible tomorrow, cosmically speaking. Dark energy drives this acceleration, pushing space to stretch faster and faster. Over unimaginable periods, galaxies will disappear beyond each other's horizons. The universe will become a lonelier place, with each galaxy isolated in its own bubble of visible space. Stars will continue burning for trillions of years, but eventually they'll exhaust their fuel. Some will collapse into black holes, others will fade into cold remnants. Even black holes won't last forever. slowly evaporating through quantum processes over time scales that make the current age of the universe seem like an instant. So even an infinite universe has a kind of ending, not in space, but in time. Not a wall or boundary, but a gradual fade into cold emptiness. Structure dissolves, energy spreads thin, and the cosmos approaches a state of maximum entropy. This transformation happens regardless of whether space is infinite or finite. The expansion continues, the cooling proceeds, the dissolution advances. In that sense, without end doesn't mean without change. It means constant, relentless change. Perhaps the real boundary isn't spatial, but conceptual. We can observe, measure, and theorize only so far before we hit the limits of human knowledge. Our instruments see a certain distance. Our mathematics describe certain possibilities. Our minds grasp certain concepts. Beyond that lies not necessarily a physical edge to space, but an edge to understanding, and maybe that's enough. Maybe the question isn't whether the universe has an end, but how far our curiosity can carry us into the unknown. The cosmos might be infinite, or it might curve back on itself in ways we can't yet detect. Both possibilities fill us with wonder, challenge our assumptions, and remind us that we're part of something far grander than anything our ancestors could have imagined. In the end, the universe without end might be less about space itself, and more about the endless nature of discovery. Each answer reveals new questions, each observation opens new mysteries, each boundary we cross shows us how much more there is to explore. When you think about the vastness above us, it's remarkable that every single star you can see with your naked eye sits right here in our own galactic neighborhood. The Milky Way galaxy contains all those visible points of light, yet it's just one among hundreds of billions of other galaxies scattered throughout space. This raises a question that has puzzled humans for centuries, whether the universe itself has boundaries or stretches on forever. The honest truth is, we simply don't know if space continues infinitely. It might go on endlessly in all directions, or it could be finite but still have no edges, sort of like the surface of a balloon that curves back on itself. Some theories even suggest our universe could be part of a much larger multiverse, with countless other regions completely disconnected from ours. Each possibility has compelling evidence behind it, but none can be proven with absolute certainty. What we do know is that the universe doesn't seem to end the way a road hits a dead end or a wall blocks your path. Instead, it offers horizons that keep expanding, vastness that refuses simple categorization. This leads us to one of the most profound questions in science. What shape is everything we know? Not the shape of individual galaxies or stars, but the actual geometry of space itself. For most of human history, space felt like emptiness, a background where matter simply existed. Einstein's theory of general relativity changed all that by revealing something extraordinary. Space isn't static, it bends and stretches and curves. Gravity isn't really a force pulling objects together, it's the result of mass warping the fabric of space and time around it. The sun creates a dip in space, and Earth simply follows the curved path that dip creates, which is why we orbit, instead of flying off in a straight line. If you extend this concept to the entire universe, the distribution of all matter and energy determines how cosmic space curves. On the largest scales, there are three main possibilities for this curvature. Space could be open, with negative curvature like a saddle. It could be closed, with positive curvature like the surface of a sphere. Or it could be flat, with zero curvature like a sheet of paper extending in all directions. Each shape implies a completely different destiny for everything that exists. Scientists debated these possibilities for decades because measuring curvature directly is incredibly difficult when you're inside the thing you're trying to measure. Then came the discovery of the cosmic microwave background, that faint afterglow left over from the Big Bang. By mapping tiny fluctuations in this ancient light, researchers could test the geometry of space itself. The results showed that the universe appears to be flat, at least within a very small margin of error. A flat universe suggests infinite extent, though it could still be finite if space wraps around itself in clever ways. Picture a video game world that seems flat locally, but loops back when you travel far enough in any direction. Space might work similarly, appearing flat in our neighborhood, while actually curving back on itself on scales too large for us to detect. To test this idea, scientists look for repeating patterns, the same galaxies appearing in different places because their light has circled around, or repeated structures in the microwave background. So far, no such patterns have been confirmed. This suggests that space is either truly infinite or so enormous that its curvature remains undetectable to us. For all practical purposes, it behaves as if it's flat, but even in a nearly flat universe, matter creates local warps in space. Massive galaxy clusters bend light through gravitational lensing, creating arcs and rings in telescope images. These distortions remind us that space isn't a static canvas, but a flexible medium shaped by whatever it contains. The balance of matter, energy, and dark energy together decides whether space curves inward, outward, or not at all. It's worth reflecting on how strange this really is. In daily life, space feels like nothing at all. You walk across a room without thinking about the geometry of the emptiness between walls. Yet, when enough mass gets involved, that emptiness itself transforms. Light bends, time slows, natural paths curve. The realization that nothingness has shape, and that this shape can change, represents one of the most profound shifts in human understanding. Some theories suggest even more complex possibilities. Space might be multi-connected, wrapping back on itself in unusual ways. Imagine walking off one edge of the world and reappearing on the opposite side, or standing in a hall of mirrors where images repeat endlessly. If space were multi-connected, light could travel paths that make the universe appear larger than it actually is. String theory proposes that our universe might be a three-dimensional surface embedded in higher dimensional space. The true shape might include dimensions curled up so small they're invisible, or vast structures extending beyond our ability to perceive them. These ideas remain speculative, but they remind us that our concept of shape might be far too limited. The geometry of everything includes not just space, but time as well. In relativity, space and time form a single fabric called space-time. The expansion of the universe is part of its geometry. The acceleration driven by dark energy is part of its geometry. Even the horizon separating what we can observe from what lies beyond is geometric. Shape isn't static, it evolves constantly, influenced by energy and matter. This affects the ultimate question of whether the universe has an end. If space is flat and infinite, it continues forever. If closed, it loops back on itself, finite but boundaryless. If open, it extends endlessly, but with different geometry. Each possibility carries implications for the cosmic future. In a closed universe, expansion might reverse someday. In an open or flat universe, expansion continues indefinitely. Current evidence points toward flatness, with acceleration, suggesting a future where expansion never stops. The shape of everything appears to be one of endless outward stretching. Galaxies drift farther apart, horizons expand, structures gradually dissolve. Over cosmic time, the shape evolves not toward collapse, but toward emptiness. This isn't a final answer because new discoveries could change our understanding, but it represents our best current picture. From a human perspective, these questions might seem abstract. Why does it matter if the universe is flat or curved, infinite or finite? The answer is that geometry influences everything else we know. The shape of space affects galaxy formation, the paths light travels, the fate of stars. It's the stage on which all history unfolds. To understand the shape of everything is to know the arena we inhabit, even if that arena is vastly larger than we can ever directly experience. There's something deeply satisfying about our ability to even ask these questions. Throughout most of history, cosmic shape was a matter of mythology. Some cultures imagined domes overhead, others pictured layered celestial spheres. Today, through careful observation and mathematics, we can speak meaningfully about the geometry of the whole universe. We can measure curvature, test theoretical models, refine our understanding. It doesn't provide certainty, but it offers remarkable clarity. When you stand beneath the night sky looking upward, you're peering into this vast geometry. The stars aren't scattered randomly, but arranged along paths, carved by space itself. The light reaching your eyes has traveled those paths, bent and stretched by the curvature of everything. You might not feel this shape directly, but it surrounds you completely. It defines how far you can see, how galaxies cluster, how time itself flows. You exist as a point within this immense structure. To wonder about cosmic shape is to recognize that you're embedded in something incomprehensibly larger, something that gives form to existence itself. When we speak of the shape of everything, we're not just describing space in mathematical terms. We're acknowledging that the universe possesses form, geometry, structure that can be studied, mapped, and gradually understood. It may be flat, curved, or stranger still, but whatever it is, it's real, and it holds all of us within its embrace. Space curves, bends, and folds in ways that completely defy what we experience every single day. When you drop something, it falls straight down. When you look across a room, light travels in what appears to be a perfectly straight line, but this everyday experience, comforting as it might be, tells us absolutely nothing about how space actually behaves on the largest scales imaginable. Einstein figured out something that sounds almost impossible. Gravity isn't really a force at all, it's geometry. Mass and energy literally warp the fabric of space and time itself. Imagine you're holding a rubber sheet stretched tight, and you place a bowling ball right in the middle. The sheet dips and curves around that ball. Now, if you roll a marble across the sheet, it doesn't travel in a straight line anymore. It follows the curves created by the bowling ball. This is exactly what happens in our universe, except the bowling ball is a star, or a planet, or a galaxy, and the marble is everything else, including light itself. The sun creates a dip in space-time, and Earth simply follows that curved path. We call it an orbit, but really, Earth is just traveling straight through curved space. Light behaves the same way. When starlight passes near the sun, it bends. This bending was first measured during a solar eclipse back in 1919. Scientists could finally see stars that should have been hidden behind the sun, but the sun's gravity bent their light around it, making those stars visible from Earth. That single observation proved Einstein right, and it opened up an entirely new way of seeing the universe. Gravitational lensing happens everywhere, in space. Massive galaxies act like cosmic magnifying glasses. They bend and focus the light from even more distant galaxies behind them. Sometimes, this creates multiple images of the same galaxy, stretched into arcs of light. Without understanding curved space, astronomers might think they're looking at several different objects, but it's really just one galaxy seen along different curved paths through space. This lensing effect has become one of our most powerful tools for exploring the universe. We can see galaxies that would otherwise be too faint to detect. Their light gets magnified and focused by the curved space around massive galaxy clusters. The universe literally helps us see deeper into itself. The concept of curved space leads to some truly mind-bending possibilities. If space curves back on itself, like the surface of a sphere, then traveling in what seems like a straight line could eventually bring you back to where you started. We experience this on Earth. Walk in one direction long enough, and you'll circle the globe. To someone who believed the Earth was flat, this return journey would seem impossible. Some models suggest our entire universe might work the same way. What appears to be infinite space might actually be finite, curved back on itself in dimensions we can't directly perceive. If this is true, then the galaxies we see in one direction might be the same galaxies we see in another direction, their light having traveled all the way around the curved universe to reach us again. Scientists have searched for evidence of this cosmic recycling. They look for identical patterns in the cosmic microwave background, the afterglow of the Big Bang. If space curves back on itself, we should see repeated patches in this ancient light. So far, no such patterns have been confirmed, but that doesn't rule it out. It just means that if the universe is curved this way, it's much larger than the part we can observe. Black holes represent the most extreme example of curved space, creating hidden destinations. A black hole is a region where matter has collapsed so completely that space curves in on itself. At a certain distance, called the event horizon, space curves so sharply that not even light can escape. From the outside, a black hole appears as a dark sphere, completely cut off from the rest of the universe. But the inside of a black hole isn't nothing. It's a hidden region of space and time, sealed off by extreme curvature. To cross the event horizon is to enter a place from which no information can ever return to the outside universe. It's perhaps the most literal example of a destination that curved space makes completely inaccessible. Wormholes are another theoretical possibility that emerges from the mathematics of curved space. These would be tunnels through spacetime, connecting distant regions of the universe through shortcuts that bypass the long journey across normal space. If wormholes exist, they would represent the ultimate hidden destinations. Doorways through curved space that could theoretically connect any 2 points in the universe. No evidence for natural wormholes has ever been found, but the fact that the equations of relativity allow for their existence shows just how flexible and surprising the universe might be. Even if wormholes don't exist naturally, the mathematics suggests that space can be folded and connected in ways that completely transcend our everyday understanding of distance and separation. Even on less exotic scales, curved space constantly hides and reveals destinations in subtle ways. When we look at a galaxy cluster through a telescope, we're seeing a complex mixture of real objects and gravitational mirages. Some of the galaxies we observe might be multiple images of the same object, created by light taking different curved paths through space. Without careful analysis, astronomers would have no way of knowing they're looking at cosmic duplicates. Space bent by intervening mass creates illusions that disguise the true nature of what we're seeing. What appears to be several separate destinations might actually be one, viewed from multiple angles through the funhouse mirror of curved space. This bending of light has profound implications for our understanding of what lies beyond the observable universe. If space curves globally, then the other side of the universe might not be somewhere else at all. It might simply be another route back to where we are. The unseen regions might be familiar territory, reflected and repeated in ways we haven't yet learned to detect. Curved space transforms our entire concept of beyond. Instead of an edge or a boundary, beyond becomes more like a fold. What is hidden isn't necessarily elsewhere. It might be a distorted reflection, brought into view by the geometry of space itself. The expansion of the universe adds another layer of complexity to this picture. As space stretches, its curvature evolves over time. In the very early universe, a period of rapid inflation may have smoothed space into near-perfect flatness on large scales, but small deviations from flatness could still remain, creating local regions of curvature. Over billions of years, dark energy has continued to shape how curvature develops. On the largest scales, space appears to be flattening. But around massive objects like galaxies and galaxy clusters, space still curves intensely. This creates a dynamic, ever-changing landscape of hidden and revealed destinations. A galaxy that's visible to us now might become hidden later as cosmic expansion carries it beyond our observable horizon. Conversely, a black hole, forming from a dying star, creates a new hidden region where none existed before. Curved space isn't static. It continuously creates and erases hidden destinations as the universe evolves. From our human perspective, accepting curved space requires a fundamental shift in how we think about reality. We're used to walking on floors, driving on roads and flying through air that all feel perfectly flat. Even the curvature of Earth isn't obvious without traveling long distances or seeing pictures from space. To accept that the very fabric of existence can bend and flex is to acknowledge that the background of reality isn't rigid. It's responsive, malleable, shaped by the matter and energy it contains. Once you accept this flexibility, the universe becomes far stranger and richer than our everyday experience suggests. Some philosophers have pointed out that hidden destinations in curved space reflect the fundamental limits of knowledge itself. There are regions we cannot see, not because they don't exist, but because the geometry of space itself conceals them. In this sense, curved space mirrors the boundaries of human perception. Just as our eyes can't see ultraviolet light without special instruments, our senses can't detect the full shape of space without sophisticated tools. Even with our best instruments, some destinations remain permanently hidden. Not due to any lack of effort or technology, but because the universe itself prevents access through the laws of physics. But curved space doesn't always hide things. Sometimes it reveals them. Without gravitational lensing, many of the most distant galaxies in the universe would be completely invisible to us. Their light would be too faint and spread out to detect. But curved space acts like a natural telescope, magnifying and focusing that ancient light so it can reach our instruments. The universe both conceals and reveals depending on how its geometry bends light and matter. This duality suggests that space isn't just a passive backdrop for cosmic events. It's an active participant, shaping what we can and cannot see through its own intrinsic properties. Astronomers have learned to read the story of curved space written across the sky. They map gravitational lensing effects, measuring the arcs and distortions created by massive galaxy clusters. They track the shapes of galaxies, using them to infer the presence of dark matter that curves space but doesn't emit light. They test models of global geometry by analyzing the cosmic microwave background radiation, looking for subtle patterns that would reveal the overall shape of the universe. This work is slow, precise, and methodical. But it's gradually revealing the true architecture of space itself. Behind all this careful measurement lies a profound truth. Space isn't empty. It has shape, structure, and dynamics that influence everything within it. That shape hides and reveals destinations in ways that constantly challenge our intuition about distance, separation, and accessibility. So when we wonder what lies on the other side of the universe, curved space offers a surprising answer. The other side might not be another place in any conventional sense. It might be a hidden reflection, a distant galaxy seen along a bent path through space, or even our own cosmic neighborhood viewed through a complete loop of curved geometry. The other side might be much closer than we think, folded into the very structure of everything around us. Curved space ensures that the universe will never be straightforward or predictable. It guarantees that mystery and wonder remain built into the fundamental geometry of existence itself. Reality might be constructed in ways that challenge everything we think we understand. Scientists have started to seriously consider that our universe, vast as it appears, could be just one small piece of something unimaginably larger. The concept of a multiverse emerges from several different areas of physics. Each branch of science seems to point toward the same startling possibility. What if everything we observe, every star, every galaxy, every particle, represents only a tiny fraction of what actually exists? Cosmic inflation offers one pathway to understanding this. In the first moments after the Big Bang, space expanded faster than light itself. This expansion happened so quickly that it defies our everyday understanding of how things move and grow. But here's where it gets interesting. This rapid expansion might not have stopped everywhere at the same time. Picture soap bubbles forming in a bathtub. Each bubble represents a complete universe. Our entire observable reality would be contained within just one of these bubbles. Meanwhile, countless other bubbles keep forming, each with its own version of physics, its own timeline, its own collection of possibilities. Some of these bubble universes might look similar to ours. Others could be so different that matter itself behaves in completely foreign ways. Stars might never form. Gravity could work backwards. Time might flow in multiple directions simultaneously. The mathematics behind this idea suggests that new universes are constantly being born. They sprout like fruit on an infinite tree, each one growing and evolving independently. Most remain forever isolated from each other, separated by expanding regions of space that can never be crossed. Quantum mechanics provides another route to multiple realities. At the smallest scales, Particles seem to exist in several states at once. They only settle into one specific state when we observe them. This leads to a profound question about what happens to all those other possible states. The many worlds interpretation suggests that every possibility actually occurs. When you flip a coin, both outcomes happen. One version of you sees heads, another version sees tails. Each quantum event creates a branching point where reality splits into multiple paths. This means there could be countless versions of Earth. In some, dinosaurs never went extinct. In others, you made different career choices, married different people, lived entirely different lives. These parallel worlds exist alongside our own, equally real but completely inaccessible. The strangeness doesn't stop there. String theory requires extra dimensions beyond the 3 spatial dimensions we experience. These additional dimensions might be curled up so small that we can't detect them. Different configurations of these hidden dimensions could give rise to universes with completely different laws of physics. Imagine a landscape with countless valleys, each representing a possible universe. Our reality occupies just one valley in this vast terrain. Other valleys contain universes where the fundamental forces work differently, where different particles exist, where the very structure of space and time follows different rules. This raises fascinating questions about why our universe seems so perfectly suited for complexity and life. The forces that hold atoms together, the rate at which the universe expands, the masses of particles, all appear fine-tuned to allow stars, planets, and eventually living beings to emerge. In a single universe, this fine-tuning looks like an extraordinary coincidence. But in a multiverse containing every possible combination of physical laws, it becomes almost inevitable that some universes will permit life. We exist in one of those rare, suitable universes simply because we couldn't exist anywhere else. The other universes in this scenario remain completely unobservable. They might be places where atoms never form stable bonds, where stars burn out too quickly, where space expands so rapidly that matter never clumps together. These realities exist in parallel to ours, forever beyond our reach. Some theorists push the concept even further. They propose that every mathematically consistent structure exists as a physical reality somewhere. This would mean that any universe you can imagine, any set of laws you can write down, actually exists in some broader framework of reality. Your thoughts themselves might represent glimpses into alternative mathematical structures, different ways that reality could be organized. The distinction between what's real and what's merely possible starts to blur when you consider such expansive versions of the multiverse. Critics point out that these ideas venture into territory that might be impossible to test scientifically. If other universes remain forever beyond observation, how can we ever confirm they exist? The multiverse might represent philosophy disguised as physics, beautiful mathematics that doesn't correspond to anything real. Supporters respond that multiverse theories emerge naturally from our best current understanding of inflation, quantum mechanics, and fundamental physics. If these theories prove correct in areas we can test, then their multiverse predictions should be taken seriously as well. The debate highlights something profound about the nature of scientific inquiry. Sometimes our theories point toward realities that exceed our ability to directly observe. We find ourselves using mathematics and logic to explore territories that no instrument will ever reach. For most people, the multiverse concept carries a different kind of significance. It suggests that reality extends far beyond our everyday experience. It implies that somewhere, in some parallel branch of existence, different versions of every possibility play out simultaneously. The idea transforms our understanding of what lies beyond the edge of our observable universe. Instead of more space containing more galaxies, we might find entirely separate realities, operating under different rules, pursuing different histories, containing different forms of complexity and beauty. Whether or not the multiverse actually exists, the concept serves important purposes. It reminds us that our theories about reality continue to evolve and expand. It humbles our perspective by suggesting that even our vast universe might represent only a small part of something much larger. The multiverse also inspires continued exploration at the boundaries of knowledge. It encourages us to keep questioning, keep building better theories, keep pushing against the limits of what we can understand about the nature of existence itself. When we wonder what lies on the other side of our universe, the multiverse offers one possible answer. Perhaps there isn't another side in any conventional sense. Perhaps there are only other realities, other expressions of the fundamental laws that govern existence, other chapters in a story so vast that our entire cosmic history represents just a few sentences. This possibility expands our concept of reality to scales that stretch the imagination. It suggests that the question isn't really about what lies beyond our universe, but about what other forms reality might take when freed from the specific constraints that shape our particular corner of existence. Quantum mechanics reveals something puzzling about the smallest parts of reality. An electron doesn't sit in one place, waiting to be found. Instead, it exists as a cloud of possibilities, spread across different locations at once. This isn't because we don't know where it is. It's because, at the quantum level, particles genuinely exist in multiple states simultaneously. When scientists measure that electron, something remarkable happens. The wave of possibilities collapses into a single, definite outcome. But here's where things get philosophically interesting. What happens to all those other possibilities, the ones that didn't get chosen? One interpretation suggests they don't disappear at all. Instead, the universe splits. Every possible outcome actually occurs, but in separate branches of reality. In one branch, you measure the electron here. In another branch, you measure it there. Both versions of you continue existing, completely unaware of each other. This idea, known as the many worlds interpretation, transforms every quantum event into a branching point. Each moment spawns countless new realities. Think about the implications for a second. Right now, as particles interact in your brain, the universe could be splitting into versions where you think slightly different thoughts. The mathematics behind this interpretation work perfectly well. Nothing about it violates what we observe. Yet, it suggests something almost unimaginable. Reality isn't one story unfolding through time. It's every possible story, all happening at once, in parallel dimensions of possibility. Meanwhile, cosmology offers a different route to multiple realities. After the Big Bang, our universe went through a period of incredibly rapid expansion, called inflation. Space itself stretched faster than light, smoothing out irregularities and setting the stage for galaxy formation. But inflation might not have been a one-time event. In some regions of a vast cosmic landscape, inflation could still be happening. These inflating regions would be separated by pockets where inflation stopped, creating what we call bubble universes. Each bubble would be like our observable universe, complete with its own Big Bang, its own expansion, its own potential for stars and planets. The space between bubbles would keep inflating forever, ensuring they never touch or interact. Our entire cosmic home, with all its billions of galaxies, would be just one bubble floating in an endless sea of similar bubbles. What makes this even more fascinating is that each bubble might operate under slightly different rules. The fundamental forces that govern physics, the masses of particles, the strength of gravity, all of these could vary from bubble to bubble. Some bubbles might have physics so different that atoms couldn't form. Others might be remarkably similar to ours. Scientists didn't invent these ideas to create science fiction scenarios. Both quantum mechanics and inflation theory were developed to explain observations. The strange implications about parallel realities and multiple universes emerged naturally from the mathematics, almost as unwanted side effects. This raises a profound question about the relationship between mathematics and reality. When our best theories point towards something unobservable, something beyond direct experience, how seriously should we take them? Are we discovering truths about the universe, or are we getting lost in mathematical abstractions? The challenge with both parallel realities and bubble universes is that they might be forever beyond our ability to test. Parallel quantum realities don't interact with each other once they split. Bubble universes are separated by regions of space that expand faster than light, making contact impossible. Yet there are hints, subtle clues that might point toward these hidden realities. If two bubble universes collided in the distant past, the impact might have left traces in the cosmic microwave background radiation. Scientists have searched for these signatures, circular patterns that could mark ancient cosmic encounters, but the evidence remains inconclusive. The fine-tuning of our universe's physical constants offers another intriguing clue. The strength of gravity, the mass of the proton, the rate of cosmic expansion, all of these seem precisely calibrated to allow stars, planets, and life to exist. Change any of them by a small amount, and the universe becomes sterile. In a single universe, this fine-tuning appears miraculous, almost designed. But in a vast collection of bubble universes, each with different physical properties, fine-tuning becomes inevitable. Somewhere among countless bubbles, one will have the right conditions. We find ourselves in that one simply because we couldn't exist anywhere else. This line of reasoning, called the anthropic principle, doesn't prove bubble universes exist, but it suggests they might help explain what otherwise seems impossibly fortunate about our cosmic home. The philosophical implications stretch beyond science into questions of identity and meaning. If parallel realities exist, then every choice you make spawns a version of you who chose differently. Every random event in your life played out differently somewhere else. There are branches where you took that job, married that person, moved to that city. There are versions of you living lives you can barely imagine. Does this make your choices less significant, knowing that all possibilities are realized somewhere? Or does it make them more precious, representing the unique path your particular branch of reality has taken? Similarly, bubble universes raise questions about our cosmic significance. If our universe is one among countless others, does that diminish its importance? Or does it highlight the remarkable fact that, out of infinite possibilities, we exist in one capable of supporting conscious observers? These aren't just abstract philosophical puzzles. They touch on fundamental questions about what it means to exist, to choose, to matter in a cosmos that might be far stranger and more populous than we ever imagined. The history of science shows us repeatedly that reality exceeds our intuitions. We once thought Earth was the center of everything. Then we learned we orbit an ordinary star. Then we discovered that star is one among hundreds of billions in our galaxy. Then we found our galaxy is one among hundreds of billions in the observable universe. Each discovery revealed layers of reality previously hidden from view. Parallel realities and bubble universes might represent the next step in this progression, revealing layers that exist beyond the reach of telescopes or any conceivable instrument. Even if we never directly observe these hidden realms, the theories that predict them continue to guide our understanding. Quantum mechanics enables the technology that powers modern life. Inflation theory explains the large-scale structure of the cosmos. These frameworks work so well in their testable predictions that their untestable implications deserve serious consideration. The search for evidence continues. New experiments probe the foundations of quantum mechanics, looking for signs that might favor one interpretation over another. Advanced telescopes scan the cosmic background radiation for patterns that might reveal ancient bubble collisions. Computer simulations explore how different types of multiverse might behave. But perhaps the most important impact of these ideas isn't technological, it's conceptual. They force us to expand our notion of what reality might contain. They remind us that the universe we observe, magnificent as it is, might be just the tip of an iceberg, whose full extent we can barely begin to contemplate. The cosmos might not just be larger than we imagine, it might be larger than we can imagine. Not just in size, but in number, in possibility, in the sheer variety of ways that existence might manifest itself across dimensions we'll never see. The human mind craves boundaries. We live in a world where everything seems to have clear limits, clear endings. Your morning coffee cup has a bottom. Your neighborhood has streets that mark where it begins and ends. Even the ocean has shores. This basic experience shapes how we think about everything, including the vast cosmos above us. But space doesn't follow the same rules as the objects in our daily lives. When astronomers talk about the observable universe, they mention a distance of roughly 46 billion light-years in every direction. This sounds like a wall, a definitive border, where things just stop. But that's not what's happening at all. Think of it this way. Imagine you're standing in a thick fog. You can see maybe 50 feet ahead before everything disappears into grey mist. That 50-foot boundary isn't a wall, it's just where your vision gives up. The world continues beyond the fog. Trees keep growing, roads keep winding, life keeps happening. The cosmic horizon works exactly like that fog. Light from distant galaxies has been traveling toward us since the universe began, but it takes time to get here. The farthest light we can see has been journeying for billions of years, and that journey defines our viewing limit. Beyond that boundary, countless galaxies continue their cosmic dance, completely unaware that we can't see them from our little corner of space. Here's something even stranger to consider. Every single point in the universe has its own horizon, its own sphere of visibility. An alien astronomer in a galaxy 10 billion light-years away would see their own cosmic horizon, centered on their position. They might be looking in our direction right now, but we're beyond their viewing limit, invisible to them just as they are to us. Each observer sits at the center of their own visible universe, like travelers in separate fog banks. The geometry of space itself plays tricks on our perception too. We're used to flat surfaces, straight lines, predictable distances. Walk forward, and you expect to keep moving away from your starting point. But space might be curved in ways that would boggle our everyday intuition. Consider the surface of our planet. If you could walk in a perfectly straight line on Earth, ignoring mountains and oceans, you'd eventually arrive back where you started. The Earth has no edge, no boundary, just continuous curved surface. Space itself might work the same way, curved back on itself, in dimensions we can't easily visualize. What feels like moving toward a distant edge might actually be a journey that curves back around. The mathematics of general relativity allows for this possibility, suggesting that straight lines in space might be more like great circles on a sphere. Black holes present another fascinating example of illusory boundaries. From the outside, a black hole appears to have a sharp, definitive edge called the event horizon. Matter falls toward it, crosses that boundary, and vanishes from our view forever. It's tempting to think of the event horizon as a physical surface, like the wall of a prison. But there's no solid barrier there, no material boundary. Instead, the event horizon marks a region where space itself is so severely curved by gravity that escape becomes impossible. If you were falling into a black hole, you wouldn't feel anything special when crossing the event horizon. No bump, no barrier, no sudden change. You'd simply continue falling. The boundary exists only from the perspective of outside observers who watch your image freeze and fade at the horizon's edge. The edge is real in terms of information and causality, but it's not a physical wall you could touch or break. Time itself seems to have boundaries that might be illusions too. We often describe the Big Bang as the beginning of everything, the moment when time itself started ticking, but physicists are increasingly cautious about calling it a true beginning. The Big Bang might be better understood as a phase transition, the moment when the universe became hot and dense enough for our current theories to describe. Before that moment lies a realm of physics we don't yet understand. Some theories suggest our universe emerged from a larger framework, a multiverse where Big Bangs happen regularly, like bubbles forming in champagne. Others propose that time itself might be cyclical, with universes expanding and contracting in endless rhythm. The apparent edge of time at the Big Bang might be another horizon, another limit of our current understanding, rather than a true boundary. The expansion of space creates its own set of illusory edges. As space stretches, distant galaxies appear to race away from us. The farther they are, the faster they recede. At some critical distance, they're moving away faster than light can travel through the expanding space between us. This creates what astronomers call the particle horizon, beyond which we can never receive signals, no matter how long we wait. But those galaxies haven't disappeared. or hit some cosmic wall. They continue existing, forming new stars, evolving, perhaps hosting civilizations of their own. They've simply moved beyond our ability to communicate with them. From their perspective, they're perfectly stationary, while we appear to be racing away into unreachable distance. This expansion is actually accelerating, driven by the mysterious dark energy that makes up most of our universe. In the far future, billions of years from now, more and more galaxies will slip beyond our horizon. Future astronomers will inhabit what appears to be a much smaller, lonelier universe. They'll see fewer galaxies, less cosmic activity, stronger apparent boundaries. The edges will seem more real to them, not because the universe has actually shrunk, but because their sphere of visibility will have contracted. These shifting horizons reveal something profound about the nature of cosmic boundaries. They're not fixed features of reality, but experiences of observers. They change with time, depend on location, and shift as our tools improve. The edge of the known universe has been expanding throughout human history. Ancient peoples saw edges just beyond the horizon of their local landscape. Medieval scholars placed boundaries at the celestial spheres. Early telescopes pushed the edge out to include other stars, then other galaxies. Each time we've developed better instruments, apparent boundaries have dissolved into new, more distant horizons. The pattern suggests that our current cosmic horizon is likely temporary too, another boundary waiting to be pushed back by future technology and deeper understanding. There's something almost poetic about living inside these nested horizons. We exist in a bubble of visibility that's constantly growing, but never complete. Like explorers in an infinite library, we can always see a little further, read a few more volumes, but never reach the final shelf. The universe keeps its ultimate secrets just beyond our reach, not out of spite, but as a natural consequence of physical law. This endless recession of boundaries has philosophical implications that extend far beyond astronomy. It suggests that our intuitive understanding of limits and edges, so reliable in daily life, breaks down when applied to the cosmos. The universe operates on scales and principles that transcend human experience. What seems like common sense, the expectation of clear boundaries and definitive edges, becomes misleading when projected onto reality's larger scales. Perhaps this is why the question of what lies beyond the universe feels so persistent and so unanswerable. We're asking about edges in a context where edges might not exist, at least not in the way we typically understand them. The universe doesn't seem to have an outside in any meaningful sense. It's not a container sitting in some larger space, it's the totality of space itself. Consider how this perspective might change our relationship with the unknown. Instead of imagining cosmic boundaries as walls that block our exploration, we might see them as horizons that invite investigation. Instead of asking what's beyond the edge, we might ask what new physics governs regions currently beyond our reach. The question shifts from geometry to discovery, from mapping borders to understanding processes. The accelerating expansion of space will eventually carry even nearby galaxies beyond our horizon. In the deep future, observers will see an apparently smaller universe, but that won't make the universe actually smaller. It will just change the view from their particular vantage point. Reality doesn't shrink when it moves beyond someone's ability to observe it. This raises interesting questions about the relationship between existence and observation. If a galaxy moves beyond our horizon, does it still exist from our perspective? Practically speaking, it becomes irrelevant to our local physics, unable to influence us or exchange information with us. But it continues its own story in regions of space-time we can no longer access. Dark energy, the force driving cosmic acceleration, remains one of the universe's deepest mysteries. We can measure its effects, map how it stretches space, calculate how it will reshape our cosmic horizon, but we don't understand what it actually is. This hidden component makes up roughly 70% of everything that exists, yet it reveals itself only through its influence on cosmic expansion and the apparent retreat of distant galaxies. The mathematics describing these cosmic horizons connects to some of the strangest ideas in modern physics. Information theory, Quantum mechanics and thermodynamics all play roles in understanding what happens at the boundaries of black holes and cosmic horizons. Some physicists even suggest that the information falling past these horizons isn't truly lost, but encoded on the horizon surfaces themselves, like shadows on a wall. These ideas push against our classical notions of what boundaries mean. Instead of sharp divisions between here and there, inside and outside, physics describes gradual transitions, relative perspectives, and observer-dependent realities. The universe becomes less like a house with rooms and more like an ocean with currents, depths, and regions hidden by distance and time. Living with these cosmic horizons requires a kind of intellectual humility. We must accept that our direct experience provides limited guidance for understanding reality's largest scales. The universe is under no obligation to conform to human intuition about boundaries and edges. Instead, we must let observation and mathematics guide us towards stranger, more wonderful truths about the nature of space and time. This doesn't diminish the human experience or make our local reality less meaningful. Instead, it places our existence within a larger context that's both humbling and inspiring. We're temporary patterns of matter and energy, conscious arrangement of atoms that can contemplate the very horizons that limit our perception. We can't see beyond the cosmic horizon, but we can't understand why it exists and what creates it. The edges we perceive in the universe tell us as much about the nature of observation as they do about the cosmos itself. They remind us that all knowledge comes from a particular perspective, limited by physical law and technological capability. Yet within those limits, we can still discover remarkable truths about reality structure and evolution. Perhaps the most profound realization is that the universe doesn't need edges to be complete. It can be finite or infinite, bounded or unbounded, and still contain everything that exists. The question of what's beyond becomes meaningless when beyond doesn't exist in any accessible sense. We're not trapped in a cosmic container, we're participants in an ongoing process that encompasses all of space and time. Thousands of years before anyone invented a telescope, people everywhere gazed upward and asked the same question we ask today. What's really out there, beyond what we can see? The night sky back then wasn't just a collection of distant stars. It was something much more alive, much more meaningful. Picture ancient Mesopotamia, where the first astronomers spent their nights watching the heavens move. These weren't scientists in our modern sense, but they were incredibly dedicated observers. They tracked every star, every planet, recording patterns that repeated season after season. But here's the fascinating part. They didn't see empty space when they looked up. They saw neighborhoods where gods lived. Each star represented a divine being. Each constellation told a story about cosmic order. The universe wasn't a vast cold expanse. It was crowded with personalities, with intentions, with messages meant specifically for humans. When these ancient stargazers wondered what lay beyond the visible stars, they imagined more divine territory, infinite realms where even greater powers resided. This gives us something profound to consider. Modern humans often feel small and insignificant when we contemplate the universe's scale, but ancient peoples felt connected, watched over, part of a grand conversation between earth and sky. Their cosmos had meaning built right into its structure. Move to ancient Egypt, and you'll find another remarkable perspective. The Egyptians looked at the Milky Way and saw a celestial river, a perfect mirror of their beloved Nile, flowing across the heavens. This wasn't just poetic imagination, it was sophisticated thinking about how earthly and cosmic patterns might reflect each other. Egyptian pharaohs didn't just rule on Earth, they expected to join the stars after death. The pyramids, those incredible monuments that still puzzle us today, were built as launching pads for this stellar journey. Beyond the visible stars lay the afterlife, not as some vague spiritual realm, but as a specific destination with geography, with routes, with procedures for arrival. Think about how different this makes death itself. Instead of an ending, death became a cosmic promotion, a graduation to a higher level of existence among the stars. The night sky wasn't separate from human life. It was the map of where everyone was ultimately headed. Ancient Greek philosophers took a more analytical approach, but their ideas were just as imaginative. Aristotle proposed that the universe consisted of crystal spheres, each one holding different celestial bodies. The stars occupied the outermost sphere, and beyond that lived something he called the unmoved mover, a perfect divine principle that kept everything in motion without itself ever changing. But Democritus had a completely different vision. He imagined infinite worlds scattered throughout endless space, each one made of tiny particles called atoms. For him, there was no edge to the universe at all, just countless variations on cosmic themes, world after world stretching forever in all directions. Here we see one of humanity's most persistent debates emerging thousands of years ago. Does the universe have boundaries, or does it go on infinitely? It's remarkable that ancient thinkers were already grappling with concepts that still challenge our best physicists today. Roman culture absorbed these Greek ideas, but wrapped them in stories that felt more personal, more dramatic. When Romans looked at constellations, they saw heroes and monsters frozen in eternal poses, divine soap operas played out across the sky. The stars weren't just distant lights. They were characters in ongoing narratives that connected to Roman values, Roman history, Roman destiny. Beyond the stars lived the gods themselves, not as abstract forces, but as personalities who took direct interest in human affairs. The night sky became a kind of divine television, broadcasting the moods and intentions of cosmic rulers who could change mortal fortunes with a gesture. Travel east to ancient India, and you'll encounter perhaps the most sophisticated cosmological thinking of the ancient world. Hindu and Buddhist texts describe universes that expand and contract in endless cycles, each cycle lasting billions of years. The stars participate in this cosmic breathing, appearing and disappearing as reality itself pulses through phases of creation and destruction. Beyond the visible stars lay multiple levels of existence, realms where souls traveled between incarnations, where different kinds of consciousness experienced different kinds of reality. The universe wasn't just big, it was deep, layered with dimensions that ordinary perception couldn't access. This cyclical vision offers a profound alternative to linear thinking about time and space. Instead of worrying about ultimate beginnings or endings, ancient Indian cosmology suggests that existence itself is more like an eternal dance, always changing but never really starting or stopping. Chinese astronomy developed its own elegant approach, seeing the heavens as a vast bureaucracy that mirrored earthly government. The emperor ruled under heaven's mandate, and the stars reflected cosmic order and balance. Court astronomers tracked celestial events, not just for scientific knowledge, but for political guidance, watching for signs that might indicate whether the ruling dynasty still had cosmic approval. Beyond the stars lay heaven itself, not as a place of reward and punishment, but as the source of legitimate authority, the cosmic civil service that kept reality running smoothly. This vision made astronomy deeply practical, a central tool for maintaining harmony between human society and universal principles. Indigenous cultures worldwide developed their own sophisticated star knowledge, often combining practical navigation with spiritual wisdom. Many Native American traditions speak of star people, cosmic relatives who maintain connections with earthly tribes across vast distances of space and time. Polynesian navigators used star positions to cross thousands of miles of open ocean. But their astronomical knowledge wasn't just technical. The stars were ancestors, guides, spiritual presences that could be consulted for wisdom about much more than just direction and weather. These navigational traditions reveal something beautiful about human consciousness. The same mental abilities that helped our ancestors survive dangerous journeys also helped them maintain rich spiritual relationships with the cosmos itself. Practical knowledge and mystical experience weren't separate categories. They were different aspects of the same fundamental human skill, the ability to find meaningful patterns in complex information. Norse mythology imagined the universe as a cosmic tree called Yggdrasil, with stars hanging like fruit from its branches. Beyond the visible stars lay multiple worlds, each populated by different kinds of beings, gods, giants, elves, humans, all connected through this vast living structure. This tree imagery suggests something profound about ancient Scandinavian thinking. The universe wasn't a machine or even a kingdom. It was an organism, something alive that grew and changed while maintaining its essential structure. Moving beyond the stars meant climbing higher in this cosmic tree, reaching branches that supported entirely different kinds of existence. African astronomical traditions, though less well documented, due to colonial disruption, reveal equally sophisticated thinking. The Dogon people of Mali possessed detailed knowledge about Sirius, including information about its companion star that European astronomy didn't confirm until the 20th century. Their traditions suggest that star knowledge came from contact with cosmic intelligences, beings who shared information about stellar systems that ordinary human observation couldn't detect. Whether we interpret this literally or metaphorically, it points to something important about human cognitive potential, our ability to intuit truths about reality that formal science later validates through different methods. What strikes me most about all these ancient perspectives is their confidence that the universe beyond the stars was populated, meaningful, accessible to human consciousness in various ways. Nobody imagined empty space stretching endlessly without purpose or content. Every culture filled the cosmic unknown with intention, with personality, with structure that made sense within their particular way of understanding existence itself. The stars weren't barriers or endpoints. They were doorways, transition zones between the familiar world of daily experience and larger realities that required different kinds of awareness to perceive. This ancient confidence contrasts sharply with modern scientific culture, where the vastness of space often feels cold, impersonal, indifferent to human concerns. Ancient peoples never doubted that consciousness and cosmos were intimately connected, that human awareness was itself a cosmic phenomenon, capable of understanding and communicating with the larger patterns of existence. Perhaps this difference reflects something we've lost as much as something we've gained. Modern astronomy reveals an incredibly rich, complex, beautiful universe, but it's a universe that seems to exist independently of human consciousness, according to laws that operate without reference to human values or meaning. Ancient cosmologies assumed that consciousness and cosmos evolved together, that the universe produced beings like us precisely because it needed witnesses, participants, conscious agents capable of recognizing and celebrating its patterns and purposes. These ancient star stories still influence us, more than we usually realize. Our constellation names come from Greek and Roman sources. Our zodiac preserves Mesopotamian astronomical observations. Our calendar systems reflect calculations originally developed by Maya, Chinese and Islamic astronomers. More subtly, these traditions established the basic human assumption that wondering about what lies beyond the visible universe is a legitimate, important activity. They normalized cosmic curiosity, making it seem natural that conscious beings should spend time and energy trying to understand the larger patterns of existence. Even our modern scientific cosmology carries echoes of ancient mythological thinking. When we speculate about parallel universes, multiple dimensions, cosmic inflation, or the anthropic principle, we're asking updated versions of the same questions that motivated ancient stargazers. We're still trying to understand what lies beyond the edge of the observable, still wondering whether the universe has purposes that connect to human existence, still using human imagination to populate the cosmic unknown with possibilities that exceed our direct experience. The tools have changed dramatically, but the fundamental human impulse remains the same. We look up, we wonder what's really out there, and we tell ourselves stories about what it all means. When we gaze up at the night sky, we're witnessing something remarkable, yet deeply incomplete. The stars scattered across darkness, the faint glow of distant galaxies, all of it represents just a tiny sliver of what actually exists. Think about that for a moment. Everything you can see, everything our most powerful telescopes can capture, amounts to less than 5% of reality. The rest belongs to what scientists call the dark unknown. Two mysterious components that make up nearly everything, yet remain completely invisible to us. Dark matter and dark energy dominate our universe, shaping every structure we observe, while staying forever out of direct reach. Back in the 1930s, an astronomer named Fritz Zwicky was studying galaxy clusters when he noticed something puzzling. The galaxies were moving far too quickly. According to everything we knew about gravity, they should have scattered apart long ago, flung into the void by their own motion. But there they were, held together by some invisible force. Zwicky realized there had to be more mass present than what anyone could see. Something was providing the extra gravitational pull needed to keep these cosmic cities intact. He called this unseen substance dark matter, and that name stuck. Decades passed before another astronomer, Vera Rubin, uncovered an even stranger puzzle. She measured how galaxies rotate and discovered that stars at their outer edges move just as fast as those near the center. This shouldn't happen. In our solar system, distant planets move much slower than nearby ones. Mercury races around the Sun while Neptune crawls, but galaxies don't follow this pattern. They spin as if surrounded by massive invisible halos of matter. These ghostly structures shape galactic rotation, binding everything together through their gravitational embrace. Without them, galaxies would simply fly apart. Today, we still can't see dark matter directly. It doesn't emit light, doesn't absorb it, barely interact with ordinary matter at all, yet its presence reveals itself everywhere we look. It bends the path of light from distant galaxies, creating cosmic magnifying glasses that let us peer deeper into space. It sculpts the largest structures in the universe, guiding how galaxies form and cluster. Computer simulations tell a fascinating story. When scientists model the universe without dark matter, they get chaos. Random structures that bear no resemblance to reality, but add dark matter to the equation, and suddenly you get the cosmic web we observe. Vast filaments of galaxies stretching across billions of light years, connected by invisible threads of this mysterious substance. The question of what dark matter actually consists of remains wide open. Leading theories suggest exotic particles that rarely interact with anything else. Some scientists propose weakly interacting massive particles, nicknamed WIMPs, that pass through ordinary matter like ghosts through walls. Others favor axions, hypothetical particles, so elusive they make neutrinos seem sociable. Underground laboratories buried deep in mountains search for these phantom particles. Sensitive detectors wait patiently for the rare moment when dark matter might reveal itself through a fleeting collision. So far, though, the mystery endures. Then there's dark energy, an even stranger puzzle that emerged in the late 19s. Astronomers studying distant supernovas expected to find that cosmic expansion was gradually slowing down, like a ball thrown upward, eventually falling back to Earth. Instead, they discovered something shocking. The expansion was accelerating. Galaxies aren't just moving away from us, they're moving away faster and faster as time passes. To explain this cosmic acceleration, scientists proposed dark energy, a form of energy woven into the fabric of space itself. Unlike matter, which pulls things together through gravity, dark energy pushes everything apart. This mysterious force now comprises about 70% of everything that exists. Its true nature remains completely unknown. One possibility is that it's simply the energy of empty space itself, an idea Einstein once considered and later abandoned. Another theory suggests it's a dynamic field that changes over time, driving cosmic evolution in ways we're only beginning to imagine. Whatever dark energy turns out to be, it controls our universe's ultimate destiny. It ensures that expansion will continue accelerating forever. The galaxies we can see today will eventually drift beyond our cosmic horizon, carried away by space itself, stretching too rapidly for their light to reach us. In trillions of years, distant galaxies will simply vanish from view, not destroyed, but erased by the relentless push of dark energy. Future astronomers, if any exist, might see only empty sky where we now observe a rich tapestry of cosmic structures. Together, dark matter and dark energy form this vast unknown majority. They're like the invisible framework of a house where we can see the furniture and decorations, but not the walls and foundation that hold everything up. We feel their presence, depend on their influence, yet cannot grasp them directly. This isn't a failure of science, but rather a profound reminder of how much remains to be discovered. The universe keeps telling us that our picture is incomplete, that what we call reality represents only the thinnest slice of the whole. Consider what this means for our cosmic perspective. Even within the observable universe, we're surrounded by the unseen. Most of what exists around us, right here and now, remains invisible. The edges of our cosmic vision aren't just boundaries of distance, but horizons of knowledge itself. Scientists continue pursuing these mysteries with remarkable dedication. Deep underground experiments wait for dark matter particles to betray their presence through rare interactions. Space telescopes map the subtle effects of dark energy on cosmic structures across billions of years. Progress comes slowly because the dark unknown doesn't reveal itself easily. Each experiment represents both hope and uncertainty. Every null result deepens the mystery, while simultaneously teaching us something new about the nature of reality. The stakes couldn't be higher, though. Understanding dark matter and dark energy means understanding most of the universe. This search also challenges our basic assumptions about knowledge itself. We often equate seeing with understanding, but cosmology operates differently. We see galaxies and infer dark matter halos. We observe cosmic expansion and deduce dark energy. Our instruments reveal effects while the causes remain hidden. We're essentially reconstructing reality from shadows, building our understanding through careful inference rather than direct observation. This might seem unsatisfying, but it actually represents one of science's greatest strengths. Knowledge doesn't always require direct sight. Sometimes the most profound truths hide behind veils of invisibility. There's something deeply humbling about this cosmic revelation. For centuries, humans believed we had a clear view of our place in the universe. First, we thought Earth sat at the center of everything. Then we learned the sun was just another star among many. Later, we discovered that our galaxy was merely one island in an ocean of similar structures. Now we're learning that even the matter we can see represents just a tiny fraction of what exists. Each step pushes us further from any notion of being central or complete in our understanding. The dark unknown serves as the latest reminder that we're only beginning to comprehend reality. Yet, there's also something hopeful in this cosmic mystery. Living in a universe where most of reality remains unknown means living in a cosmos full of infinite possibilities. The dark unknown isn't a dead end, but a frontier waiting to be explored. Discovery is far from finished. Someday, dark matter and dark energy may yield their secrets. When they do, our understanding will expand again, just as it has with every previous cosmic revelation. Until then, we're left with this beautiful paradox. What we cannot see shapes everything we can observe. The dark unknown reminds us that the universe is far richer and stranger than we can currently picture. It shows us that our place in the cosmos is small, but our capacity for wonder remains vast. Even in an age of advanced instruments and elegant theories, mystery still beats at the heart of existence. Perhaps that's exactly as it should be. A universe without mysteries would be a universe without frontiers. The dark unknown ensures that science will always have new horizons to explore, new questions to ask, new revelations waiting just beyond the edge of current understanding. Space stretches in ways that challenge our everyday understanding of distance and time. When light leaves a distant galaxy, it begins a journey through an expanding universe, where the very fabric of reality grows larger with each passing moment. Think of it like trying to swim upstream in a river that keeps flowing faster. Even light, traveling at the ultimate speed limit of the universe, sometimes cannot overcome this cosmic current. The balloon analogy helps us picture what's happening, but the reality runs deeper. As space expands, it doesn't just move galaxies apart, it also stretches the light waves traveling between them, a photon that starts its journey. As visible blue light might arrive at Earth, stretched into infrared, carrying the signature of its long voyage through expanding space. This stretching tells us stories about time itself, about how the universe has grown during the billions of years that light spent crossing the void. Our local neighborhood remains relatively stable, held together by gravity's firm grip. The Milky Way, Andromeda, and dozens of smaller galaxies form what astronomers call the Local Group, a gravitationally bound island in the expanding sea of space. These galaxies dance around each other, sometimes approaching, sometimes receding, but always remaining within reach of each other's gravitational influence. In about 4.5 billion years, something remarkable will happen. Our galaxy and Andromeda will collide, not in a violent crash, but in a slow, graceful merger lasting hundreds of millions of years. Stars will be flung into new orbits, new spiral arms will form, and eventually, the two galaxies will become one. Some call this future galaxy Milkomeda, a name that captures the cosmic marriage of our galactic homes. But beyond our local group, the rules change completely. Galaxy clusters drift apart, like islands in an ocean that keeps getting wider. The space between them grows, carrying them away from each other at speeds that increase with distance. The farther away a galaxy sits, the faster it recedes. Not because it's moving faster through space, but because there's more expanding space between us and it. This expansion creates something profound, the cosmic horizon. Just as Earth's horizon limits how far we can see across the ocean, the cosmic horizon limits how far we can see into space. Light from galaxies beyond this boundary will never reach us, no matter how long we wait. The expansion of space ensures that their photons, racing toward us at light speed, never gain ground in their journey. They're like runners on a treadmill that speeds up faster than they can run. What makes this even more striking is that the horizon itself is shrinking. Galaxies visible today will eventually cross this boundary and disappear from view forever. Their light, already stretched thin by billions of years of cosmic expansion, will fade until the last photon reaches us. After that, nothing, no new light will follow. No new information will arrive from those distant worlds. Future astronomers, living in a universe billions of years older than ours, will inherit a much lonelier sky. Only the merged remnant of our local group will be visible, floating in what appears to be an empty cosmos. They might conclude that their galaxy is the entire universe, unaware of the vast cosmic web of galaxies that we can still observe today. The evidence for the Big Bang, for cosmic expansion, for the rich history of structure formation, will have literally moved beyond their reach. This creates a strange temporal privilege. We live at a special time when the universe reveals its secrets generously. The cosmic microwave background still glows faintly in every direction, carrying information about the universe when it was only 380,000 years old. Galaxy surveys map the large-scale structure of the cosmos, showing us how matter clumped together over billions of years. Deep space telescopes peer back toward the Big Bang itself, catching glimpses of the first stars and galaxies forming in the young universe. Consider the philosophical weight of this timing. If conscious observers had emerged much later in cosmic history, they would face a universe seemingly empty and static. The very questions that drive modern cosmology, about origins and evolution and the nature of space-time, might never occur to them. Their night sky would offer few clues about the dynamic, expanding, evolving cosmos that we can still witness. The light reaching us from the most distant observable galaxies began its journey over 13 billion years ago, when the universe was less than 1 billion years old. These ancient photons carry information about galactic nurseries, about the first generation of massive stars, about how heavy elements were forged and scattered into space. We're not just seeing distant places, we're seeing distant times, witnessing the universe's childhood through light that has traveled since before Earth existed. But for every galaxy we can observe, countless others remain forever hidden beyond our cosmic horizon. They exist in regions of space-time that are causally disconnected from us, meaning no information can ever travel between us and them. These unseen galaxies might harbor different conditions, different histories, different outcomes of cosmic evolution. Perhaps they contain structures unlike anything in our observable patch of the universe. The mathematics of cosmic expansion guarantees this hidden majority exists. Our observable universe, vast as it seems with its 100 billion galaxies, represents only a finite bubble in what may be an infinite cosmos. The bubble's edge is defined not by any physical barrier, but by the interplay between the age of the universe, the speed of light, and the rate of cosmic expansion. This limitation applies equally to any observer anywhere in the universe. Hypothetical astronomers in those unreachable galaxies face their own cosmic horizon, can see their own finite patch of the cosmos, and remain forever unaware of our existence. The universe fragments into countless overlapping but distinct, observable regions, each containing a unique view of the cosmic whole. The expansion that creates these horizons is driven by something mysterious, dark energy. This invisible component makes up about 70% of everything that exists, yet we understand almost nothing about its true nature. We know it causes the expansion of space to accelerate. We know it will determine the ultimate fate of the cosmos, but its fundamental identity remains one of the deepest puzzles in physics. Dark energy's influence grows stronger over time. As the universe ages and matter becomes more diluted, dark energy's repulsive effect dominates more completely. This means the cosmic horizon will continue to shrink, and more galaxies will slip beyond our reach. The process is irreversible, a one-way journey toward cosmic loneliness. There's something both humbling and beautiful about existing at the boundary between the knowable and unknowable. We can push our instruments to their limits, build telescopes that capture the faintest whispers of ancient light, and still know that more lies beyond our reach than within it. The universe keeps its secrets not out of malice, but as a consequence of its own fundamental structure. This cosmic hide-and-seek extends to the very beginning of time itself. Even our most powerful telescopes cannot see all the way back to the Big Bang. There's a wall of opacity about 380,000 years after the beginning, when the universe finally cooled enough for atoms to form and light to travel freely. Before that moment, the cosmos was opaque to electromagnetotrate. Hot, dense plasma that light could not penetrate. The cosmic microwave background represents this ancient wall, the afterglow of the moment when the universe became transparent. It's the oldest light we can ever hope to see, with traditional telescopes, a baby picture of the cosmos when it was less than 1% of its current age. What happened in those first 380,000 years remains hidden behind this wall of ancient fire. Yet even this limitation points toward new possibilities. Gravitational waves, ripples in space-time itself, might carry information from even earlier epochs. Neutrinos, ghostly particles that barely interact with matter, could preserve messages from the first seconds after the Big Bang. The universe may be secretive, but it's not completely silent about its origins. Perhaps the most profound aspect of unreachable galaxies is how they redefine the meaning of existence itself. These cosmic islands continue their evolution, form new stars, host planets, possibly even nurture life, all without any possibility of communication with our part of the universe. They represent a pure form of existence, neither observed nor observable, yet undeniably real. Physics stands as our finest lens for peering into the workings of everything around us. The equations it provides describe how things move, how energy flows, how light behaves, and even how space and time bend and stretch. From something as simple as a falling apple to something as vast as entire galaxies moving apart, physics finds the hidden connections, the patterns that turn confusion into clarity. But here's something that might surprise you. Physics doesn't just tell us what we can discover, it also shows us where our knowledge hits a wall. The universe isn't simply a giant puzzle, where every piece can eventually be found and fitted into place. Some questions, no matter how much we advance, may never have answers we can reach. Consider what we know with remarkable certainty. The universe is expanding, and we know this because when we look at distant galaxies, their light appears red-shifted. This tells us that space itself is stretching between those galaxies and us. Not only is the universe expanding, but that expansion is actually speeding up, driven by something we call dark energy. Galaxies aren't scattered randomly either. They form intricate web-like patterns, shaped by the gravitational pull of dark matter. Then there's the cosmic microwave background, a faint glow that fills all of space. This radiation is the cooled remnant of an incredibly hot, dense early phase of the universe. It carries information from when the universe was only a few 100,000 years old, like a baby photo of the cosmos. These aren't educated guesses or theories we're still testing. These are measured facts, supported by data from multiple independent sources. The tools of physics let us extract knowledge from signals that have been traveling for billions of years. We can reconstruct cosmic history from the faintest whispers of ancient light. It's almost like cosmic archaeology, but instead of digging through dirt, we're digging through time itself. Physics also lets us peer into possible futures. With our discovery of accelerated expansion, we can predict that galaxies not gravitationally bound to our local group will continue moving away until they disappear beyond what we call the cosmic horizon. We can estimate that stars will eventually burn through all their fuel and fade away, leaving behind remnants, white dwarfs, neutron stars, and black holes. Over even longer timescales, those black holes themselves will slowly evaporate through something called Hawking radiation. They'll release their energy bit by bit until nothing remains but thin, scattered radiation. This isn't wild speculation. It follows logically from the laws of physics as we understand them, extrapolated across unimaginably vast spans of time. Yet physics also shows us exactly where knowledge must stop. We cannot see beyond the observable universe, because light from those distant regions simply hasn't had time to reach us yet. Physics assures us that those regions exist, governed by the same laws we see operating here, that direct knowledge of them is permanently cut off. No matter how perfect our instruments become, no matter how long we wait, there will always be regions that remain forever unobservable. The universe itself creates this boundary between what can be known and what cannot. It's not a limitation of our technology or our intelligence. It's built into the very structure of reality. Another fundamental limit lies at the very beginning of everything. The Big Bang model describes the universe when it was extremely hot and dense, but only after a certain point in time. As we try to trace things back toward time zero, our equations simply break down. At what's called the Planck time, roughly 10 to the minus 43 seconds after the beginning, our physics no longer applies. General relativity and quantum mechanics, our two most successful theories, cannot yet be unified into a single framework. What happened before that moment, if the word before even makes sense in this context, is hidden from us. Physics suggests possibilities like cosmic inflation or bouncing cosmologies, but it cannot yet tell us definitively what occurred during those first impossible fractions of a second. This isn't a failure of scientific creativity, it's a fundamental limitation of our current theoretical understanding. Even within the space we can observe, there are things we may never truly know. Consider dark matter, for instance. We infer its existence from its gravitational effects on visible matter and light, but its true nature remains one of the biggest mysteries in physics. Experiments continue searching for direct detection, but it's entirely possible that the particles or phenomena responsible are simply beyond our technical reach. We may never build detectors sensitive enough to capture dark matter directly. Similarly, dark energy is even more elusive. We know it drives the accelerated expansion of space, but whether it's a cosmological constant, something more dynamic, or something else entirely, remains unclear. It may be that dark energy's nature cannot be pinned down precisely, that it's woven into the structure of space itself, in ways we can only approximate, never fully grasp. There are also limits imposed by chaos and complexity. Physics can describe the fundamental laws that govern matter and energy, but in systems with countless interacting components, prediction becomes practically impossible. We know the equations that describe how fluids flow, but we cannot predict every swirl and eddy of turbulence in a rushing river. We understand the laws of chemistry, but we cannot forecast the exact path of every molecule in a drifting cloud. On cosmic scales, this means we may understand the overall behavior of galaxies and galaxy clusters, but not the precise history of each individual star, or the exact motion of every particle. Physics gives us the underlying structure, the rules of the game, but it doesn't erase complexity. Some details are forever beyond our reach, not because the laws are unknown, but because the outcomes are too intricate to track completely. The quantum world introduces yet another kind of fundamental limit. Quantum mechanics allows us to calculate probabilities with extraordinary accuracy, but it does not allow certainty about individual events. We can predict how likely an electron is to be found in a particular region of space, but we cannot say exactly where it will be at any given moment. We can calculate the half-life of a radioactive isotope with incredible precision, but we cannot predict the exact moment when any particular atom will decay. Physics reveals the patterns, but denies us the specifics. Knowledge itself becomes probabilistic, rather than absolute. This isn't a gap in our understanding that will eventually be filled. As far as we can tell, it's built into the fundamental structure of reality itself. The universe operates on probability at its deepest level. Then there are questions of ultimate scope that may forever remain open. Is the universe infinite or finite? Does space curve back on itself, or does it stretch endlessly in all directions? Physics suggests various models, but it also acknowledges that observation may never settle these questions definitively. If the universe is vastly larger than the portion we can observe, we may never detect its true overall shape or size. The multiverse remains another tantalizing possibility. Physics suggests mechanisms through which multiple universes could exist, perhaps through eternal inflation or quantum branching into parallel realities. But whether these other universes are real may never be confirmed or denied. These ideas may remain forever at the border between what physics suggests and what cannot be known, no matter how far our science advances. This tension between knowledge and limitation isn't a flaw in science. It's actually part of its greatest strength. Physics is refreshingly honest about what it can and cannot answer. It doesn't pretend that every question has a solution just waiting to be discovered. Instead, it carefully marks boundaries. It says, here is where the data takes us, here is what we can confidently claim, and beyond this line, we simply do not know. For some people, this might feel frustrating, but in another sense, it's actually liberating. It shows us that curiosity never truly ends, that mystery is built into the very structure of existence itself. There's also a deeply human side to this contrast between the known and unknowable. The things physics has already revealed to us are genuinely staggering when you stop to think about them. The idea that light has been traveling through space for billions of years before reaching our eyes. The fact that galaxies formed from tiny fluctuations in the density of the early universe. The reality that space itself is expanding, carrying distant galaxies away from us. The strange truth that black holes slowly evaporate over unimaginable time spans. These are extraordinary insights that reveal a universe far more surprising, vast and intricate than earlier generations could have imagined. But the things we cannot know are just as meaningful in their own way. They remind us that the universe is not small enough to be wrapped neatly in our theories. No matter how elegant or powerful those theories become, reality remains larger, deeper, and stranger than complete understanding would ever allow. From one perspective, the things we will never know may actually outnumber the things we can discover. There will always be galaxies beyond our cosmic horizon, regions forever unseen and unseeable. There will always be scales too small, processes too complex, or phenomena too elusive to measure directly. There will always be beginnings and endings that remain beyond the reach of our current theoretical frameworks. But this doesn't make our hard-won knowledge any less valuable or remarkable. If anything, it makes it more precious. To understand even a small fraction of the universe is extraordinary, given its incredible scale and complexity. To know its fundamental laws at all is almost miraculous when you consider how recently humans developed the tools to discover them. Physics suggests not certainty, but wonder. It's grounded in solid evidence, rigorous mathematics, and careful observation, yet it remains open to acknowledging its own limits. In our daily lives, we rarely think about these cosmic boundaries. We live in a world where questions usually do have answers, where problems typically have solutions. But when you step into the realm of cosmology and fundamental physics, you enter a domain where limits are woven into the very fabric of reality itself. The edge of the observable universe isn't a line we can eventually cross with, better telescopes. It's a fundamental limit imposed by the finite speed of light and the finite age of the universe. The Planck time isn't a gap we can fill with greater cleverness or more sophisticated mathematics. It represents a genuine boundary where our best theories collide and break down. Dark energy isn't simply a puzzle missing just one crucial piece. It's a reminder that reality may have layers and aspects we cannot fully uncover, no matter how hard we try. Physics functions as both a lantern and a horizon. It illuminates vast territories of knowledge while simultaneously showing us the edges beyond which that illumination cannot reach. So when we ask what physics suggests versus what we can never know, the answer reveals itself as beautifully complex. Physics suggests a universe that's expanding and accelerating, structured by invisible dark matter, driven by mysterious dark energy, and filled with billions of galaxies containing countless stars and planets. It suggests universal laws that operate everywhere, elegant equations that describe motion and energy across all scales of space and time. It suggests a future where galaxies drift apart into cosmic isolation, where stars eventually burn out and fade, where even black holes slowly evaporate into nothing. But physics also reveals the fundamental limits of knowledge itself. It shows us that some regions of space are forever unreachable, that some moments in cosmic history are permanently hidden, that some questions may never yield their secrets. Both sides of this cosmic equation are part of the same profound truth. Physics illuminates reality, while simultaneously defining the shadows where illuminates cannot penetrate. When most people think about science, they imagine precision, definitive answers, and the steady accumulation of facts. Most people think of science as pure logic, cold facts, measured observations. They imagine researchers in white coats, carefully recording numbers, following strict protocols. Science seems like the enemy of creativity, bound by rules, limited by what can be proven. But this picture misses something fundamental about how discovery actually works. Every scientific breakthrough starts with someone wondering about something that doesn't make sense. Why do things fall down instead of up? What makes the stars shine? How can something be in two places at once? These questions don't come from data. They come from curiosity, from the ability to imagine that reality might be stranger than it appears. Think about how we figured out that time isn't constant. Einstein didn't discover relativity by staring at clocks all day. He imagined what it would be like to ride alongside a beam of light, to watch lightning strikes from a moving train. These thought experiments, these acts of pure imagination, led to equations that changed everything we know about space and time. The quantum world presents us with phenomena that seem impossible, particles that exist in multiple states simultaneously, objects that tunnel through solid barriers, measurements that change reality itself. Early physicists couldn't just accept these observations. They had to imagine entirely new frameworks for understanding existence. They had to picture a universe where common sense doesn't apply, where probability replaces certainty. When we look out into space, we see galaxies rushing away from us in all directions. The obvious explanation might be that we're at the center of some cosmic explosion, but it took imagination to realize that space itself could be expanding, that the universe could be growing like a balloon being inflated. This wasn't obvious from the data. It required creative thinking to even consider such a possibility. Dark matter makes up most of the universe, yet we can't see it directly. Dark energy drives cosmic expansion, but we don't know what it is. These aren't things we stumbled upon, they're concepts that scientists imagined to explain observations that didn't fit existing theories. Someone had to picture invisible matter threading through galaxies, unseen forces pushing space apart. The search for life beyond Earth relies heavily on imagination. We design experiments to detect biosignatures we've never seen, on worlds we can barely observe. Astrobiologists imagine ecosystems based on different chemistries, life forms that might thrive in conditions we consider hostile. Without this creative thinking, we'd never know where to look or what to look for. Consider how we study the smallest particles in nature. No microscope can show us individual quarks or electrons directly. Instead, we imagine them as tiny spheres, as waves, as vibrating strings. These mental pictures help us make sense of mathematical equations. They give form to abstract concepts that exist beyond our direct experience. Technology emerges from this same creative process. Every invention begins as an imagined possibility. Someone pictures a machine that could fly, a device that could calculate, a telescope floating in space above the atmosphere. Engineers then figure out how to make these visions real within the constraints of physical laws. When scientists detected gravitational waves for the first time, they weren't just confirming Einstein's equations. They were proving that space itself could ripple like water, that massive objects could create distortions we might someday measure. This required both mathematical precision and the ability to imagine space as something flexible, dynamic, alive. The cosmic microwave background radiation fills the entire universe, a faint glow left over from the Big Bang. But recognizing this radiation as the afterglow of creation required imagination. Someone had to picture the early universe as hot and dense, then imagine how that primordial fire would look today after billions of years of cosmic expansion. Particle accelerators smash atoms together to create conditions that existed microseconds after the Big Bang. This isn't just about building bigger machines, it's about imagining what those first moments of existence might have been like. Scientists envisioned particles that existed for tiny fractions of a second, forces that shaped reality before stars or planets could form. The Higgs boson was predicted decades before we could detect it. Physicists imagined a field that gives mass to other particles, then designed experiments to find evidence for this invisible influence. They had to picture something that permeates all of space, but leaves only the subtlest traces of its existence. String theory proposes that the fundamental building blocks of reality are tiny vibrating loops too small to ever observe directly. This idea emerged from imagination, from asking what might exist at scales beyond our current ability to measure. Whether it's correct remains unknown, but the creative thinking drives new mathematical tools and experimental approaches. When we wonder about parallel universes, we're engaging in structured imagination. The mathematics of quantum mechanics and cosmology suggest that other realities might exist alongside our own. We can't visit these other worlds, but we can imagine what they might be like, how they might differ from the universe we know. The edge of the observable universe marks the limit of what we can see, but not the limit of what might exist. Beyond that horizon, space could continue forever. It could curve back on itself. It could branch into dimensions we can't perceive. These possibilities emerge from imagination guided by mathematical consistency and physical principles. Every failed theory teaches us something valuable. The luminiferous ether was imagined as the medium that carried light waves, but experiments proved it doesn't exist. This wasn't wasted creativity. It was necessary exploration that cleared the way for better understanding of how light actually behaves. Science fiction often inspires real science by imagining technologies and discoveries before they become possible. Satellites, submarines, rockets to the moon, all appeared in stories before they appeared in reality. The boundary between disciplined imagination and creative speculation is fluid, each feeding the other. Climate science requires us to imagine how Earth's atmosphere might change over decades or centuries. We picture greenhouse gases trapping heat, ice sheets melting, weather patterns shifting. These aren't direct observations, but projections based on understanding how complex systems behave over time. The search for extraterrestrial intelligence combines rigorous science with creative thinking about what alien civilizations might be like. We imagine how they might communicate, what technologies they might use, how we might recognize their presence. This speculation guides real research, determining where to point our telescopes and what signals to seek. Brain research involves imagining how consciousness emerges from neural activity. We can measure electrical impulses and chemical reactions, but understanding how these create thoughts and feelings requires creative leaps. Scientists picture information flowing through networks, patterns emerging from chaos, awareness arising from complexity. Synthetic biology allows researchers to design living organisms with new capabilities. This requires imagining how genetic circuits might work, how biological systems could be rewired, how life itself might be programmed like software. The boundary between engineering and evolution becomes a space for creative exploration. Perhaps imagination serves science, because both are fundamentally about pattern recognition. We look for connections between seemingly unrelated phenomena. We search for underlying principles that explain diverse observations. This requires the ability to see beyond surface appearances, to picture hidden relationships, to imagine unity beneath apparent chaos. The collaborative nature of science means that imagination spreads from one researcher to another. An idea proposed in one paper inspires questions in another. Failed experiments suggest new approaches, mathematical insights reveal unexpected possibilities. The scientific community becomes a collective imagination, exploring possibilities no individual mind could consider alone. This interplay between creativity and evidence, creativity and evidence, creativity and evidence, creativity and evidence. Unlike pure mathematics or abstract philosophy, science must constantly check imagination against reality. Unlike pure engineering or applied technology, science must constantly imagine new possibilities beyond current capabilities. It occupies a middle ground where dreams meet data, where vision encounters verification. We exist in a cosmos where boundaries define everything. The observable universe stretches out for tens of billions of light years, but that edge isn't just a distant marker. It's a fundamental part of who we are. These cosmic limits don't just sit out there in space, waiting to be discovered. They actively shape how we live, how we think, and how we understand our place in existence. Consider the Big Bang for a moment. This wasn't just some explosion that happened long ago. It's the reason you can see stars when you look up at night. Without that hot, dense beginning, matter would have stayed spread out, cold and lifeless. No galaxies would have gathered together. No stars would have ignited. The atoms in your body, the oxygen you breathe, the carbon in your cells, all of it depends on that cosmic boundary between a time before stars and the time we live in now. The speed of light creates another boundary that touches your life every single day. When you step outside and feel the warmth of the sun on your face, you're experiencing light that left the sun 8 minutes ago. Those distant stars twinkling overhead, they're showing you images from years, decades, even centuries in the past. You never see the universe as it actually is right now. You see it as it was, filtered through time, delivered to you at light, steady pace. This creates something profound. Every glance upward gives you history. The present moment you experience is actually woven together from countless moments in the past. It's like living in a museum where every exhibit updates itself, but always shows you what came before, never quite catching up to now. Gravity shapes our lives in ways we barely notice. It keeps you planted on the ground, obviously. But it also determines the conditions that make life possible. Earth orbits the sun at just the right distance because of gravitational forces that were set in motion billions of years ago. Yet gravity also traps us here, in this one small corner of the cosmos. To leave Earth takes enormous amounts of energy. To reach even the closest star would require thousands of years with our current technology. We dream about traveling to other worlds, other galaxies, but those dreams exist within the firm boundaries of physics. Gravity and distance create a kind of cosmic neighborhood. We can see out, but we can't easily leave. It makes us local beings, rooted in one particular spot, even as we gaze at an infinite sky. Stars themselves have limits that directly affect our future. Our sun burns bright and steady now, but it won't last forever. In a few billion years, it will start to expand, growing hotter and larger. Eventually, it will shed its outer layers and fade to a white dwarf. All life on Earth is tied to this timeline. We exist not just because of cosmic beginnings, but within the framework of cosmic endings. The same processes that created us also ensure that nothing lasts forever. Dark matter and dark energy sound like abstract concepts, but they shape our daily reality. Dark matter holds galaxies together. Without it, the Milky Way would have scattered long ago. Stars wouldn't have had time to form and evolve. Planets wouldn't have developed stable orbits. Dark energy pushes the universe apart, determining how the cosmos will end. These invisible forces remind us that most of what shapes our world can't be seen directly. The psychological impact of these limits runs deep. Knowing that we can't see beyond a certain horizon changes how we think about everything. It humbles us, showing us that what we know represents only a tiny fragment of what exists. But it also sparks our imagination. The boundary itself creates the desire to reach past it, even if we can only do so in thought. The fact that we can't observe what happened before a certain point in cosmic history doesn't end scientific inquiry. It launches new theories. Ideas about inflation, multiple universes, bouncing cosmologies. Limits don't silence curiosity. They provoke it. The boundaries become starting points for new questions, new investigations, new ways of understanding. There's comfort in limits too. A universe with no boundaries at all might feel overwhelming, disorienting. Limits give structure to existence. A beginning gives us a story we can tell. Horizons give us a sense of scale we can grasp. The speed of light creates order, preventing events from happening in chaotic, contradictory ways. These cosmic boundaries influence how we think about our own mortality. Stars are born, live their lives, and die. Galaxies drift apart over vast stretches of time. Nothing in the universe lasts forever, and that includes us. But this impermanence also creates value. If everything lasted forever, would we treasure individual moments the way we do? The fleeting nature of existence, from stars to planets to lives, makes them precious. The limits of the universe connect us to each other in unexpected ways. Every person on Earth shares the same cosmic horizon. We all receive light from the same distant galaxies. We all puzzle over the same mysteries of dark matter and dark energy. The boundaries of knowledge are universal. They form common ground across all cultures and generations. It's tempting to think of limits as purely negative, as things that prevent us from going further or knowing more, but limits actually create possibilities. Without gravity, matter would never have clumped together to form stars and planets. Without the speed of light limit, cause and effect would collapse into chaos. Without beginnings and endings, there would be no cycles, no evolution, no change over time. Our knowledge grows within the framework these limits provide. We can't see past the cosmic horizon, so we focus our attention on what we can observe. We can't measure events before a certain point in cosmic history, so we develop better theories to approach that boundary. We can't easily travel to distant stars, so we build telescopes and space probes to extend our reach in other ways. The universe's limits guide human creativity. Every discovery we make happens within an awareness of where the boundaries are. Scientists work at the edges, pushing against the limits, finding new ways to explore within the constraints that physics provides. These boundaries also fuel our imagination about what might exist beyond them. The cosmic horizon makes us wonder about other regions of space, other universes, other dimensions we can't access. The unknown period before the Big Bang makes us consider alternative ways the cosmos might have begun. The gradual fading of distant galaxies beyond our reach makes us imagine futures very different from the present. By preventing us from seeing everything at once, limits ensure we never stop asking questions. Curiosity stays alive because there's always more to wonder about, always another boundary to approach, always another mystery just out of reach. So while the boundaries of the cosmos seem distant and abstract, they're actually woven into everything we experience. They set the conditions that make life possible. They shape how science develops. They influence our sense of time and meaning. They connect us through shared mystery and wonder. Living in this universe means living with limits. Far from being disappointing, these boundaries give structure to existence, create a frame for wonder, and remind us that we're part of something much larger than ourselves. Every piece of knowledge we gather reveals how much more remains hidden from view. The concept of infinity usually feels distant, something that belongs in textbooks or mathematics classes. We think of endless numbers, equations that never resolve, distances our minds can barely process. But infinity isn't just scattered across the far reaches of space. It weaves back through our daily existence in ways we rarely notice. When we gaze upward at night, we're participating in humanity's oldest conversation with the unknown. Ancient civilizations saw patterns in the stars, not just points of light, but stories about existence itself. They understood something we sometimes forget, that looking outward automatically turns us inward. The same questions that drove them to build observatories still pulse through our thoughts today. Our position in the cosmos seems almost laughably small. One planet, circling an ordinary star, in a galaxy among billions of others. Against such scales, we might feel reduced to nothing. Yet flip that perspective slightly, and something remarkable emerges. Out of all the possible ways matter could arrange itself, here we are. Conscious beings capable of asking these very questions. The universe didn't just create galaxies and stars. It created minds capable of wondering about galaxies and stars. This recognition changes everything. We're not separate from the infinite cosmos, observing it from outside. We're participants, woven into its fabric. Every atom in our bodies was forged inside dying stars, billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it emerged from nuclear furnaces scattered across space and time. Time adds another layer to this puzzle. Stars burn for billions of years. Galaxies evolve across even longer spans. Our individual lives flicker by in mere decades. Against such temporal vastness, we might seem insignificant. But consider what happens in those brief decades. We compress billions of light years into thoughts we can hold. We imagine stellar life cycles spanning eons. We picture cosmic expansion stretching space itself. The human mind performs this miraculous compression constantly. We cannot live as long as mountains, but we can study their formation. We cannot travel to distant galaxies, but we can map their positions. Through thought and imagination, we bring infinity into ourselves. The boundary between inner and outer space becomes surprisingly fluid. There's something almost paradoxical happening here. The more we learn about cosmic infinity, the more we discover unreachable regions, impossible distances, potential multiverses beyond counting. Yet this expanding sense of the infinite pushes us to value finite moments more deeply. If galaxies will eventually drift beyond our view, then tonight's stars become precious. If our time under them is brief, then sharing that time gains weight and meaning. Scientists who study the overview effect, that transformation astronauts experience when viewing Earth from space, describe a profound shift in perspective. Seeing our planet as a small blue dot suspended in cosmic darkness creates awe, but also connection. Boundaries that seemed important from ground level dissolve. The infinite doesn't diminish us, it reveals our participation in something magnificent. This awe operates through imagination as much as observation. Infinity isn't something we can walk across or touch directly, but we can picture it, wonder about it, stretch our minds to accommodate it. Every time we imagine what lies beyond the visible horizon, we're bridging the gap between data and meaning. Telescopes extend our senses, but imagination connects us to the cosmos in ways no instrument alone can achieve. Dark matter and dark energy remind us that most of reality remains invisible. We can measure their effects, observe how they shape galaxies and drive cosmic expansion, but their true nature stays hidden. This isn't a failure of science, it's a feature of existence itself. The universe maintains mystery as an essential ingredient. Light carries information across space, but it takes time to travel. There will always be regions beyond light's reach, not because our instruments aren't powerful enough, but because the structure of space-time itself creates boundaries. Physics breaks down at the earliest moments after the Big Bang. Some aspects of cosmic origins may remain forever inaccessible to direct investigation. These limits aren't obstacles to overcome, they're part of the framework within which knowledge operates. Mystery isn't the opposite of understanding, it's understanding's companion. Every great discovery begins with questions that acknowledge the unknown. Astronomers didn't start with knowledge of distant galaxies. They started with puzzling smudges of light, Physicists didn't begin with theories about dark energy. They began with observations that didn't match expectations. The same patterns that govern cosmic evolution also shape our personal experience. We live within horizons, finite lifespans, boundaries of comprehension. We don't always understand why events unfold as they do, why certain choices lead to particular outcomes, why some things endure while others fade. The mystery that surrounds galaxies also surrounds our daily lives. When we think about alternate possibilities, paths not taken, different versions of ourselves that might have been, we're engaging with infinity on a personal level. Just as physics imagines parallel realities, we imagine alternate histories. The infinite in science mirrors the infinite in consciousness. Both circle back to fundamental questions about identity and existence. Every culture that has ever looked upward has grappled with these same mysteries. The stars we see tonight are the same ones that guided ancient navigators, inspired medieval philosophers, and puzzle modern cosmologists. The shared experience connects us across time and geography. The infinite sky belongs to everyone, creating bonds that transcend individual differences. Curiosity operates in natural rhythms, expanding outward through questioning and imagination, then returning inward to rest in wonder. This cycle doesn't diminish discovery, it sustains it. Without periods of rest, curiosity burns out. With rest, it gathers strength for future exploration. The pause between questions is as important as the questions themselves. Tonight, the mystery that surrounds cosmic infinity also surrounds each of us. We don't need to solve it immediately. We can dwell within it. The unknown isn't emptiness waiting to be filled. It's abundance waiting beyond our current reach. Accepting mystery allows curiosity to remain alive without demanding immediate closure. The other side of the universe may always remain beyond our direct knowledge, but that unknown space isn't a limitation, it's possibility itself. Room for imagination, for science, for wonder, for connection. The boundary we cannot cross gives meaning to everything on our side of it. The questions we cannot fully answer make the questioning itself worthwhile.
you.